In this video, we are going to teach a robot how to walk. This one, exactly. And we are going to use AI for this. And to explain this process, we will start with something super simple, which is handwriting recognition, correct?
That's right. We're ready to go on showing how to first detect some handwriting. Then we'll kind of go a little bit more into how neural networks work, just to demystify them. They're not black magic. And then we'll switch into making this thing walk.
And making it walk, it means it will teach itself how to walk.
So what we're going to do is we're going to use a computer model to simulate it just inside the computer. And we'll do millions and millions of simulations here live on a GPU. And then it'll learn how to walk inside the model. And then we'll just take that recording of it walking and put it back in the robot.
Cool. So basically, it starts with no idea how to walk. It will try all the kind of combinations. And it will basically teach itself how to walk. And then we will upload it to real hardware and we will see it's really walking. Ah, cool. Exactly. Okay, so let's start with this handwriting recognition.
Okay, awesome. So to kick off on this kind of process, the first thing we want to really learn about is neural networks. Obviously that's all the rage nowadays, and an important element of how to teach a robot how to walk is the neural networks that drive it. So one of the basic examples that you can find a lot of samples of online is how to recognize handwriting. So that's a kind of a simple demonstration that anybody can run on their laptop. That doesn't take too much time, doesn't take too much to learn, and the data is readily available, so you can get this running in just a few minutes, really. But what it'll do is it'll kind of teach us a bit about how neural networks can recognize images and make predictions based off of those images. We'll dive a little bit deeper into just the mechanics. So instead of treating the neural network as a black box that we don't know what's inside of it, we can kind of talk about what's really happening on the inside, at least with the simple neural networks. And with that, once we kind of understand what neural networks are and how they work, how they're trained, we can jump to the next application, the reinforcement learning problem of making something learn how to walk, where the neural network tries and tries and tries to walk, and it gets rewarded for either actually moving forward or not. And over time, it gets better and better at fulfilling this task and eventually learns how to walk. And of course, we can transfer that to real hardware.
Okay. So, and we are going to use, I think you mentioned a microcontroller for this, for the handwriting.
Yeah, so obviously with this being a hardware channel, it's nothing without hardware. So what this is basically our version of an OpenMV. So I should say, so my name is Sergiy Nesterenko. I run a company called Quilter.ai, where we try to automate layout for circuit boards. And so this circuit board was actually laid out with an AI. It's just a copy of an OpenMV, which is an open source design. And we simply took that design and, deleted the layout, redid the layout ourselves and made it work.
So your AI did the layout. You design some kind of application or software which is AI driven and doing PCB layout, correct?
That's exactly right. Yeah. So we have a website, Quilter.ai, where we currently have people on a wait list. So if anybody wants to see what AI does with their layouts, please check it out. But for the sake of this video, all that we really need to know is that it's a STM32 microprocessor. It's got a camera right here. It's got an SD card to store the weights of our neural network. We'll get into what that means. You can pop a screen on here, but we don't need one today. And it's got USB to connect to the computer. Mm-hmm. And so after we train the neural network to recognize handwriting just in in our desktop, we will then take that neural network and put it onto this STM32 to actually do the recognition.
Okay, and if someone would like to try this, what kind of board they can buy? I think, can we find it on the internet?
Certainly. So openmv.io is the website where they make these. These are awesome, by the way. This one right here is the one that we're basically using, this OpenMV Cam H7. But check out OpenMV. They've got a ton of different open source designs, even some that have a lot more kind of horsepower for doing computer vision applications. And they have a lot of demos. I mean, handwriting I kind of chose because a very, very simple neural network can do a pretty good job at it, so that we don't have to dive into the more complicated neural networks. But there's a lot of demonstrations that recognize speech and gestures and stuff like that. And also they pair this with Edge Impulse, where you can kind of just upload data and allow that website Edge Impulse
I've
to
done
train
a video. It should be published right now, but today we are not going to use Edge Impulse. We are going to do it which way? Something
we're just going to do it from scratch.
What are we going to use? I don't know.
So we'll use Python as the programming language of choice. That's kind of the de facto language that everybody uses for deep learning, almost everybody. And then what we'll do is we will use a library called TensorFlow, which I'll explain more the details of why it's important and how to use it to train it from scratch. And
so this is the Google open source or free stuff. Okay.
Correct. Exactly. Yep. So Google, this was one of the first deep learning libraries that has a whole lot of kind of features built in to build and train neural networks. Totally open source, anybody can run it. And so we'll use that. And the reason I'm doing that rather than Edge Impulse is I really want to show the details of what these neural networks are and what they're doing.
Okay, let's do it.
So that you can kind of see. Let's do it. Cool. So the first thing I'm going to do is, in case anybody wants to replicate any of this code, on my GitHub, I have a public repository named after you, Robert, that just has all of these demonstrations. So all the code is here, open source. Anybody's welcome to it. Please have at it. The other thing I wanted to do to make this easier is to run everything with Google's Colab website. The reason I'm doing this is that Colab is basically a server that runs on Google's cloud that you can just come sign up and use immediately. And that way you don't have to do any of your own installation or configuration. You don't have to install Python. And most importantly, one of the things that tends to get beginners caught a little bit is how to install a GPU driver correctly to work with deep learning libraries. That could be a little bit of a pain sometimes. So with Colab, nothing is needed. You just come to this website, you can take my notebook directly and you can run it yourself. And I believe you can do it for free, even without paying for anything to Google.
So you just go, or you need Google account, I guess, and then you can just start it. It's kind of like virtual machine or something like that.
Yeah, exactly. Yeah, they basically, the website itself shows what's called a notebook. If you just search Google Colab, C-O-L-A-B, you'll definitely find it. And once we start running it, Google will spin up a virtual machine within their servers, and then that virtual machine will be dedicated to us doing this kind of training here.
And everything is pre-installed, so everything will just work same way as what we will be showing here in this video. Okay.
Exactly right.
Perfect.
Exactly right. So first, I'll just go through roughly, how the whole setup works, and then we'll dive into the details after we kind of show the whole demo.
Okay.
So first things first. So this is a notebook. In a notebook, everything is run one cell at a time. Each cell just has Python. So you're writing regular Python, but a notebook makes it a little bit easier to run little bits of Python at a time and kind of like introspect and see what's happening inside of each piece. So the first thing I did is I just, pulled in the different libraries that we need. So TensorFlow is the one that we're going to be using to do the deep learning stuff. Matplotlib is just for plotting pictures, and NumPy is just a math library to help us with some math functions. Second thing we'll do is we'll make sure we actually have a GPU. So when I run this little function, it shows us, yeah, we really have a GPU attached, and here it is. And you can see Colab even shows us, here's our utilization, here's how much GPU we're using, disk, so on and so forth. We can ignore that.
I have a question.
Sure.
So when you start Colab, it's like empty, and then you add these blocks?
Yeah. So the way I'd recommend for anybody who wants to play with this to start, actually, is to go to this repository that I made. You can simply click on Handwriting, and so this notebook is here. But what you can do is you can just click right here to open it in Colab.
Okay.
And it'll just set it all up for you.
Perfect.
Okay. So the next thing we'll do is we'll actually get the handwriting data set. So like I said, handwriting is a good example because it's literally the hello world of the deep learning problems. It's, everybody knows it. Everybody starts with it. It's a very, very easily available data set. With TensorFlow, it literally comes built in. So you just, call for this data set. It'll download it real quick, and then now the computer has it. And so we'll take a look at what's in there.
Question. So data set, I guess it's the bank of all the kind of handwritings from all the kind of different people?
Yes.
Okay.
So more explicitly, to show you literal examples, we'll go through a list of 10 examples of the individual data points and labels. So I should mention, we're doing supervised learning. So supervised learning is in a case where you have many, many pieces of data and labels for that data. So in this case, we literally just have handwritten numbers. So somebody wrote this 5, and we turned it into an image. And there's a label, so a truth that this is actually 5. Somebody wrote a 0, and we have a label that it is actually 0. Somebody wrote a 4, and a label that it is actually a 4, so on and so on and so on.
But this is not in the data set. These are just images what we are going to test with the data set. These are the images which are going to recognize, or?
So what we're going to do is we're going to use these images. There's about 60,000 of them here to teach the neural network how to recognize.
Oh, okay, so these are images from the data set.
Correct.
Okay, I understand.
Correct. And then what we'll do is I'll set up my iPad in a little bit, and then I'll actually just write with my own hand these different numbers, and then we'll see that the neural network can recognize numbers that it hasn't seen before.
Okay.
That's kind of the important part. It's not so hard to make something that recognize exactly what was seen before. You could just memorize how the pixels are arranged and memorize the label. That's trivial. It's more interesting to see a slightly different 4 than you've ever seen, or a slightly different 3 than you've ever seen, and still get it correctly. That's kind of where the magic of neural networks really, really happens, if you can do that successfully.
Okay.
All right, so that's what we have in this data set, is just a bunch of these pictures and a bunch of labels for what they are. So to mention what the shape of this data set is, so this data set is something called a tensor, which is just a fancy word for like an abstracted matrix. So it's a 3-dimensional matrix where we have 60,000 pictures, and each picture is 28 by 28 pixels. And each pixel is just some number from 0 to 1, representing black or white. So to show it even more explicitly, this is literally one example from that data set, right? So we literally have an array or a list, depending what language you use, and just a bunch of numbers. So all the black pixels are just zeros, and then later on, these pixels start to gain some white value, and so on and so on and so forth. So what we're really showing the neural network is just this list of numbers, where each number is some pixel that we're reading from. Okay. So next what we'll do is we'll actually create the neural network. And I'll go into more detail for what this means and what these different layers are and everything like that. But for now, all you really need to understand is that a neural network is just a function. So it's just a function, just like, y equals sine of x or something like that. But it has a few kind of special properties. So the most important property is that the function is configurable. So we have a whole bunch of numbers that, independent of the data coming in, change what the function does. So you can think of like, y equals mx plus b is just a function that is a straight line. Your m and your b are configurable variables that change how the x converts into the y. So your m is slope, b is intercept. And by changing those two numbers, you can then fit a line to some data. This is the same kind of thing, just this function is more complicated than a simple line. It has more bells and whistles, but not a whole lot more complicated. So we'll go into that a little bit later.
I have a question before we go. So if someone would like to use their own pictures, then they will create their own dataset. Dataset is just a bunch of pictures, correct?
Yes, in this case, yes.
Yeah, and then you need to somehow convert them into these metrics?
Yeah, so the pictures themselves are already just a list of numbers.
Okay.
Right. So when you take a picture on your phone, if you open up the JPEG and undo the JPEG compression, you literally just have a set of kind of XY positions for the pixels, and then some typically red, green, blue value for each pixel. In a lot of cases, it's simpler to just make it black and white. That way you don't have to worry about the different colors. So now you just have X, Y position for all the pixels, plus just a number from 0 to 1 or 0 to 255 that tells you if the pixel is black or white or somewhere in between.
But if you would like to do it by yourself, then there are already some applications which can do this, or?
Yeah, good question. So in Python, there's a good library called Pill. So what this will do is this will gives you all sorts of different techniques for manipulating pictures. But what you can do within the most basic sense, I don't know if they have an example here, maybe not. But what you can do within the most basic sense is like literally take a picture with your cell phone, save it as a JPEG or PNG or any other format. And then when you open up Python, you can open it with Pill. And then what Pill will do is it will know how to read that file format, that JPEG or PNG, and it will return just the list of pixels. And so now you have this kind of tensor or this matrix, which is just a list of numbers.
Okay, we can continue.
Yeah. Yep. Okay. So we'll touch more into the neural network later. But just to show the example, so when we start with a neural network, we have all of these configurable parameters, but they are all initialized almost randomly. So the network isn't really going to do anything useful. It's just going to basically take some input, do some random manipulations, and effectively produce a pretty much random output. So just to show that real quick, we can take our model. So our model is just a function, and we can feed it the first data point. So xtrain is our list of all of the training samples that we want to train the neural network on. We'll just take the first one, and we'll make predictions. And for the predictions, what we actually get is a list of 10 numbers. So this is kind of important to understand. The way that we're going to predict which actual digits we are seeing in the picture is by outputting a distribution. So the first number, what it represents is after we apply this softmax operation, this first number here represents the probability that the number is 0 in the picture. Then this is the probability that it's 1, probability that it's 2, probability that it's 3, so on and so forth, until the probability that it's 9. And so this is, in the sense, in the supervised learning problem called a classification problem, where we have 10 classes, namely the 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are just trying to predict the probability that the image we are being shown is in a specific class, like 0 or 1 or 2 or so on and so forth. So that's what the network is doing. It's taking an image as an input. So in this case, 24 by 24 pixels, or sorry, 28 by 28 pixels. And it's outputting 10 numbers that are the probabilities of each class. And then whichever class is the highest probability, that's the one that we think is the number.
Okay. I'm curious how you are going to train it.
That's the fun part. So the next thing we'll need to define is what's called a loss function. So a loss function you can think of as kind of a critic. So what it does is it looks at the prediction that the neural network made, and it looks at the correct label. So let's say the neural network predicted 4 and the correct label was 5. And it measures how wrong the neural network is. So in that case, what we would have wanted to see for the label 5 is 0, 0, 0, 0 for the first 4 labels, 0, 1, 2, 3, 4, or first 5 labels, and then a 1 for the 5 label, and then zeros for everything else. And really, the neural network outputs something like this, where all the numbers are relatively uniform, bunch of point ones. And so this loss function, this categorical cross entropy, basically measures how far away this distribution of numbers is from the correct number of distributions.
So in the first step, we will get the predictions, like I think this is the probability of each number, and then we run something else on these results to kind of correct them or trying to correct them.
Exactly.
Okay.
That's exactly right. And the way that we know how to correct them is with this number called the loss, which tells us how incorrect the neural network was. So if the network gave us the correct result, there's no need to correct it. We make zero change. But if it made a very incorrect result, then we do want to change. And
how do you know what you are going to change?
We'll get into that. That's a little bit more involved, but for now, I just want to show the whole process so you have an idea of the big picture. And then the slides here I have on the right will go into what's the actual math of making the changes. Okay, so the next part is to choose an optimizer. So this is kind of starting to get at what is going to be happening with how to make the corrections. And for now, the basic way to think about it is what the optimizer is doing is something called gradient descent. So this loss kind of tells us over the space of all configurations for this neural network, where is the neural network really wrong for our data set and where is the neural network really right for the data set. And what we want to be is where it's really right, so where the loss is as low as possible. So the same way that you can kind of take a ball and go to the mountains, put it at the top of the mountain, let it go, and then the ball will roll to the lowest part of that valley, we're going to do the same process. But the ball, in our case, is going to be the configuration or the weights of the neural network. And this optimizer is going to be what kind of simulates gravity, what points it in the right direction and lets it roll to the bottom. And again, we'll get into the details there later.
That's nice explanation, because when I had the first video about machine learning, this was quite complicated to understand, but I like your explanation because when we are in the mountain and when we put this ball somewhere, we don't know even which direction it will go, and there may be multiple valleys. So sometime it may go there, sometime it may go somewhere else, and you still may need a couple of tries to actually find the valley which is the lowest one, correct?
100%. Yeah, so what you're hinting at is this problem of local and global optima. It's a very important concept. And so it's in general in optimization, in any kind of optimization, and in this case, we're optimizing a neural network, but in any kind of optimization problem, finding a local optimum or the local valley is really easy. You just roll the ball down the hill. But recognizing that you might have to go up a mountain first and then go down to find a lower valley, that's really hard. And so, deep learning researchers have found all sorts of tricks, all sorts of ways to kind of encourage the optimization engine to go and look for those global valleys. And in a nutshell, this is breaking down into a kind of distinction between exploration and exploitation. So when you're just exploiting, you're just rolling down to the closest point. But when you're exploring, you're allowing yourself to make moves that seem not good in order to explore some new area. Mm-hmm. And this trade between how do we balance exploring and exploiting is one of the most difficult parts of all reinforcement learning and supervised learning research. It's kind of very critical at the core of what a good ML practitioner can do is balance those two variables.
Okay, but if I understood right, you basically always start with some kind of random numbers which will place your ball somewhere in this whole mountain, and then you just leave it run?
Exactly.
Okay.
Exactly. The numbers that we start with in the network are not totally random.
Okay.
People have some clever techniques for how to choose a type of random distribution that isn't good for your problem, but is amenable to kind of learning. But beyond the scope of this video, this certainly would work okay, even if we started with fully uniformly random weights. And yeah, this process will find good weights.
Okay.
Or good configuration.
Okay, let's continue.
All right. So let's see. I think I haven't been running these, so let's just keep doing that. So there's our predictions. There's our loss. In the notebook, I had already run this previously, so you're seeing my old outputs, but I'll just rerun them while we're at it.
Where do we see some outputs?
Yeah, so I should have pointed that out. Below every cell of code, so this is a little cell of code with this little run button. Underneath that is the output for that cell.
Okay.
Yeah, so this tensor, when you think of tensor, just think vector or think matrix or the 3, 4, 5-dimensional version of those two.
Yeah, I can't imagine 5-dimensional, but okay.
Yeah, that's okay. You don't really have to. You can think of like if you think of an image, that's 2 dimensions. If you think of a video, now it's 3, and so on and so on and so forth. but that's okay. That's not important. So this is the prediction tensor. So that was that list of different probabilities for each class. Well, these aren't probabilities yet. Different outputs from the neural network for each class. We turn that into a probability with the softmax function. It's just kind of an exponential function that always sums to 1, and all probabilities must always sum to 1. So that's what this does. And then we have our categorical cross entropy loss, which compares two distributions and determines how different they are, which boils down to a single number. So right here, for this one prediction, we just have a number 2.5, right? Your distributions are 2.5 away from each other. So then we make our optimizer and we compile the model. So typically, it takes a lot of computation to train one of these neural networks. And so you want to make that as efficient as possible. So one way to make it efficient is to do what's called compilation, just like compiling some C code, where you can give your code to an optimizer that will figure out how to combine operations in a way that is as efficient in memory and compute as possible. And in this case, we're actually running this all on GPU. Now, GPU for this problem is overkill, but for making the robot walk, it's kind of necessary. And GPUs are really, really, really good at training neural networks because they're just really good at executing a lot of linear algebra, which is mostly what the neural networks are. So now we've compiled this whole structure that has the actual model where we want to tune the weights, this optimizer that kind of simulates gravity, simulates where the ball will roll, this loss function, which tells us how incorrect we are, and we did compile everything. So this is kind of what's going to allow us to run the iteration.
I have another question. So do you run this only for one image or for all the images? Or?
Great question. So that is in the next cell. So in this next cell, so we now have this compiled model, and that's kind of what we're going to train, but we haven't run it yet. We've just prepared it.
Mm-hmm.
In this next cell is where we're going to run it. Oops, we don't need that. So this model.fit, the word fit is the same fit that maybe when you learned linear regression in school, when you fit a line to some data, it's exactly that. And so here we choose how often to run it. So the first thing we're doing when we do fit is we actually point it at the data we want to use. So in this case, xtrain is our variable that holds all of the images. In this case, of 60,000 of them. ytrain holds all of our labels. In this case, there are 60,000 individual numbers that correspond to the correct answer. Then we have this variable called epochs. And an epoch is representative of running the training on an entire data set. So we have 60,000 images, and we're going to show those 60,000 images to this neural network 100 times.
Okay.
So it's really, 6 million images that it will see.
Okay.
Over the course. So this is kind of the key thing that is very different about humans versus neural networks today is neural networks need ludicrous amounts of examples to learn from in general. And this is an active problem. So researchers are trying to figure out, how does a human learn to recognize numbers by seeing a few of them, whereas a neural network needs millions and millions and millions of examples. But for today, that's kind of the important piece. So we have 60,000, but we're going to show the same image over and over again 100 times.
So it means it adjusts the function, and then we show the same image again, because after we change the function, it may get better or worse. And okay.
Yeah, exactly. So what we'll do is, but we do it 100 times in kind of in order. So we go through all 60,000 images, not quite one by one, but batches at a time. I'll talk about that in a second. And we update the weights, update the weights, update the weights, update the weights. Then we've done one epoch or one iteration. Then we just restart. And, if you have the same number that you showed first, but then you change the weights 59,000 more times, showing that number can actually be useful because the neural network might forget how to correctly predict that first number.
I understand.
And this is also an important problem is if you have a very, very large data set, how do you not forget kind of what you taught it for the first ones? And so you want to make very, very small changes basically as you go. So it kind of keeps a memory of all of the different pieces in a nutshell.
So in the steps before, we actually prepared some kind of initial model or?
Yes. Exactly.
Okay.
Yep. So the model is just a function. It just takes images as an input. It spits out a number as an output, and it's configurable. And at this point, the configuration is totally random.
Okay.
And so what we now want to do is find the configuration that predicts the correct label for every point in our data set.
Okay.
And then the other variables here that I'll point out is we have a validation split, which I'll get into more in a second. But basically, you want to reserve some part of your data set to not train your network, but to evaluate your network. Because the critical thing we're going for is we're not trying to memorize the correct answer for 60,000 numbers. That's really easy to do, and it's not impressive in any way. What we really want to do is when the network sees a previously unseen number, we want to make sure that that is predicted correctly. This is called generalization. Really important, also difficult and important concept. So what we do is we cut our data set into an 80-20 split where 80% of the data is going to be used to actually update the configuration, actually update the weights. And 20% will be used for us to see if it's actually getting the correct answer on samples that the network has never seen during training. So it's really just to help us make sure that we are not memorizing, but rather generalizing. And then the last variable here is called batch size. This basically makes training faster by doing many images at once. So instead of running one image at a time, the GPUs are more effective if you put together 2,400 images and then run all of them at exactly the same time. And it can the GPU is just a lot better at exploiting all of its power to do that kind of in parallel and speed up the training.
That's interesting because I would expect you adjust the weight every time you run one image. So I'm not sure how you update it after you run 2,000 images at once.
Yeah, that's a very interesting question as well. And in some cases, it might be better to run one image at a time. So this is another thing that a machine learning engineer will kind of tune, where if you're doing too many images at once, the way that you update your weights might be too big or kind of too coarse. But you can still kind of the easiest way to think about it is like, since we're doing 2,000 images at once, we basically have kind of like 2,000 models or 2,000 mountains that we're looking at the same time. And for each one, we're computing the direction for which the ball should roll down. And you can basically just average them and take that next step in a simple sense. Now, if the mountains are totally different, then that's not going to work. But our hypothesis here is that there exists a single set of weights or a single configuration or a single valley in that mountain range that is really good at predicting all of these numbers. So hopefully all of these vectors kind of point in roughly the same direction.
Okay, I understand.
That's kind of how you can think of it.
So you can run them all at once because in some cases you are expecting to get very similar results. Okay.
Yeah, because ultimately we're not training 2,400 different neural networks. We're training one.
Yeah.
And so all the configuration has to be the same across all these numbers. And we're looking for the overall optimum for all of those numbers at once.
Yeah, I understand. Okay.
Yeah. So let's run that real quick. So thankfully with GPU, this should be fairly quick. It'll run through it and maybe take just a minute here. And so each time you're seeing this epoch update, we've shown the network 60,000 images.
It's really quick.
It's really quick. Yeah. That's definitely the cool part. So, of course, if you were to do this with, like ChatGPT, where you have this gigantic network with hundreds of billions of parameters and you have 1 trillion examples of words and all that stuff, you need tens of thousands of GPUs and months of training, right? So this isn't always like this. But the good thing about this example is that it is very quick and very easy. Okay. That's why it's a good place to learn, because you're not spending a lot of time just waiting for it. All right, so we're done. A couple of things to note as we ran is we should see our loss, which is kind of the error on average for the numbers throughout that epoch, decrease. So that's kind of that function of how different is the probability distribution compared to what it should be. We should see the accuracy, which is literally, did you get the right answer or not? That should increase. So ideally, it should go close to 1. And then here we have the validation loss and validation accuracy. This is us evaluating that same network against the data on which we didn't train. There's some nuances here, but basically in a good case, we should also see the validation loss decrease, and we should see the validation accuracy increase. So this is basically telling us that the network is doing something good, even with images it has never seen. And so if we scroll down, roughly speaking, we see that the loss is going from 1.27 at the beginning down to 0.0062. So something happened. Accuracy on the images that we trained on is 99.81, and the accuracy on the images we did not train on is 98.1. So in this case, we're kind of seeing that our network seems to memorize a little bit the images that it's seen, but when it comes to images it hasn't seen, it's not quite accurate. As good on the images.
Yeah, it's not as accurate because it's only 98 and there is 99, but it's I guess it's still a good number, or I don't know.
It's pretty good. I mean, it depends on your application, right? If this is USPS and you need to have every number correct to make sure that you send it to the right person, maybe 98% is not so good.
Yeah, auto driver for cars, yeah.
Right, yeah, let's make it better than 98, right? But if you're just doing a YouTube video and showing how it works, 98 is great.
Okay, so what do we do now?
So now, again, kind of an important part of this is to take a look at what happened. You look at these two curves. So these are the curves that we showed. This is just accuracy. So the blue curve is our accuracy of the actual model that we trained on going up. And the validation curve is on the images that we haven't seen before. And we can kind of see that at some point, we can get the training curve close to 1, but not the validation curve. And that tells us a little bit about how to make this model better that we can talk about later. But in a nutshell, this is a good result, right? We started with random actions and we ended up with 98% accuracy. Okay, good enough.
You know what is interesting? That the initial values for the unrecognized or not trained data set, it's like very high, the accuracy, 0.88.
I should mention that I believe that these numbers get measured after the first epoch.
Okay.
So you're not seeing
the first one.
Random.
Okay.
Yeah.
The zero one.
The first fully random one. Yeah, it should be lower.
So even after like first run, it's starting to be better than just guessing.
Oh, much better. Yeah, much better. So even having just seen 60,000 images, the validation set, we're already getting to 87%, 88%. For totally random model, you would have expected like 10% accuracy, right? If you're just guessing.
Yeah.
And if your data set has a even distribution of all the numbers, right? If our data set had all 7s and we just guess 7 every time, okay, we'd have 100% accuracy, but that's not the point, right? So in this data set, the nice thing is somebody made sure that there's a good even split of all the numbers. And so then a random guess would give you about 10% accuracy. And so even seeing all the pictures once, we're already getting to 87%. So it's not too bad.
Okay.
So let's go to a little bit more evaluation. So this is just kind of showing the same information we've already seen before. So for the evaluation, the test set. So I should mention, to make it more clear, another good practice is to actually even have 3 different data sets. So you can even have a training set that you're actually updating the weights on, a validation set where we can plot these curves as we train. But as a human, you are part of the learning loop, because what we can do is once we look at the validation, we can then go and tweak the model and tweak the model and tweak the model to drive the validation number up. And sometimes we might accidentally trick ourselves into thinking that we did a really good job because validation is now getting close to 1, but actually maybe now we're kind of picked some arbitrarily good parameters that happen to perform well in the validation data set. So we're fooling ourselves, and that's really not good. So a good practitioner will also set aside a whole 3rd data set called the test set that you don't kind of keep in this iteration loop, and you test only at the very end to really make sure that the numbers are still good for a totally unseen data set.
After the 100 iterations, you use this one.
Yeah, exactly. And so we're kind of just seeing that that is also still performing well, 98.2% accuracy. This confusion matrix is a nice visualization for any classification problem. And it shows us roughly how correct our network is in certain cases. So what we're seeing here is on one axis, we have the correct result. So if the number should have been 0 or 1 or 2 or 3 or 4, 5, 6, 7, 8, 9, through 0. And on the other axis, we see the prediction. And what we see is if the prediction matches the correct number, we add 1 on the diagonal. So this is how many times we predicted 0 and measured 0. This is how many times we predicted 1 and the correct answer was 1. This is how many times we predicted 2 and the correct number was 2, so on and so on and so forth. But over here, you see mistakes. So this, we predicted 1, but the correct number was 0. And so we saw one example of that happening in our test.
So from this matrix, you can actually see where it is making mistakes.
Exactly. And so that can also give you a little bit of insight into what's happening. The tricky thing about this kind of programming is that, if you're used to writing code for microcontrollers or just any kind of code, up until this point, your process is somewhat straightforward. You have some requirements, you write some code, you see a bug, you print out some variables, you find that bug, and you iterate, right? Not to trivialize that, but that's kind of how the workflow works. And typically when something breaks, it's very obvious that something is not working correctly. The robot turns right instead of left, or there's an error, or something like that. Something crashes, there's a stack overflow, With neural networks, that is not the case. Neural networks, they can have those errors, and those errors are easy to fix in general. The hard errors to fix are where it seems to be running correctly, but actually something went horribly wrong. And so they fail silently. So you could be thinking that you're doing everything fine. Everything could look like it's running okay. The GPU is busy. It's doing math. Everything looks okay, but actually it's not learning. And so the hard part about AI and machine learning is to kind of ask the question, like, what's actually happening with the math? And is the math doing what you expect? And so that's why I'm showing these kind of different tools and graphs that are important to understand, because when your results don't look good, when your results are saying 10% and it's not improving, it's not a bug that just explodes and you have to go fix with some print statements. It's a bug in that your math is wrong. And so you have to really understand all the different parts of the math and see where you made a subtle mistake. You had a negative where you should have had a positive, or you're dividing by something, or not converting to a probability, or many things could be going wrong. That's kind of the important part.
So you need to basically also analyze the whole bunch of results, not only if the prediction was correct or not. Yeah.
Exactly. So the practitioners, what they end up doing is they make plots of the actual configurations and the weights to see how they're changing. They try to visualize the whole network to see which parts of the network are activating, which parts of the network are staying stale. There's all sorts of techniques. You can even do things like showing the network an image and then have it highlight for you which part of the image it was most sensitive to. So which parts of it are triggering to get some intuition, lots and lots of tricks. But that's kind of where this craft, this skill shows up, is in this ability to disassemble a network and understand the different pieces and try to understand why it's not performing as well as you want.
Okay, we can move to the next step.
Okay, so now we have a neural network. It's performing well to our standards for predicting images it hasn't seen. So let's put it on a microprocessor. That's the next part.
Okay.
That's the fun part. Let's get it to work. So the first thing we'll do, so OpenMV, the camera that I showed, they have a whole lot of code written for working with TensorFlow, which is awesome. So you can basically just train a network, stick it into your firmware, and it'll figure out how to run it and feed the images to it and all that stuff. So great job on their part. We don't have to do any of the kind of crazy heavy lifting of figuring that out. The only thing we got to do is we have to shape our inputs in the way that the camera outputs them. So basically speaking, the OpenMV camera outputs images in a 3-dimensional entity where you just have a single element that is the picture. and we train the network as a two-dimensional entity where it's just a picture, not inside an array. So to our model, we add this simple reshaping operation that just like converts the tensor into the correct dimensions. But the information is still exactly the same. So nothing has really changed at this point. Then we do what's called quantization. So in a nutshell, what this does is we trained this network with large floating point values, in particular with floating point 32 values. In some cases, it makes sense to even train with float 64, or if you dare, you can train with float 16, to make it less. But issues can happen when you do that. We can go into later if we want. But float 32 is an expensive operation, and to make it fit on a microprocessor, we can actually reduce this a little bit. And so what this will do is this will take the same network and find for us the most similar network where all of the information that's happening is happening in int8s, in 8-bit integers rather than 32-bit integers. So we're effectively reducing the size of the network by a factor of 4 and making it way faster to run, while still keeping it almost exactly the same.
That's interesting. Is it because float is easier to create a model and experiment with it, and you could theoretically also do it in this 8-bit int, but maybe you would get inaccurate results or something?
That's exactly right. So hypothetically, of course, you can train this with 8-bit int all the way through, but where the problem comes up is in how we do that ball rolling down the hill. Because we have to compute a lot of derivatives, and we'll show the math and the details of this in a little bit. And when you stack a lot of them, when you have a network that's deep in that it has many deep layers, you're multiplying a lot of numbers, and with ints, they can quickly kind of overflow or have too low a precision or go to 0. And if all of your gradients go to 0, just because your error, you've gotten to the point where you don't have enough bits, you have no learning.
Yeah, I understand.
And so floats allow you to keep very, very, very small numbers that are near 0, but not quite. Whereas ints quickly collapse to 0, and that's it. You don't know where to go. So that's kind of the issue is, it helps to have more precision when you train, because the math involved in training requires higher precision.
Okay, I understand.
But for inference, this is fine. It's not nearly as, you don't need to compute gradients anymore. And so for inference, it's usually okay to kind of approximate with 8-bit integers.
So once you have the finished model, you can actually transfer all these results, which are floating numbers. You can basically somehow replace them with similar integer numbers.
Yeah, exactly.
Okay.
Exactly. Yep, exactly. And then the final step is just to save the model. So we're going to save the model as this TF Lite, TensorFlow Lite representation, and just going to write it to a disk, and then we'll transfer it to our microcontroller.
And this is a library, or what is it?
It's actually literally just a binary file.
Okay.
So here it is. Let's actually download it real quick. But the information that it contains is what is the structure of the model. So like what were the different layers that we had, and we'll talk about layers. But what are the different layers that this model has? So the sequence of operations that we need to perform from input to output. And then what are all of the configurations for each of those operations? So that information is all in this, I think it's a binary, it might not be binary, but it's all just in this file. And then the OpenMV library will know how to open this file, how to extract the model setup, how to extract the weights. So this basically tells our microprocessor exactly how to take this final model at the end of training and how to use it to make predictions.
Okay. I'm curious because, so you are going to use some kind of STM environment to load this, or how do you load this binary?
Yeah. Let's show that. So again, another nice thing here for people who don't want to go too crazy with this stuff is OpenMV has their own, whoops, I shouldn't have closed that, has their own nice IDE to take care of this for you. And they make it really, really, really nice. So if you buy one of the OpenMV boards, you will get this software where you can write code and interact with the board, see the images that it's seeing and all that stuff very, very easily.
That's interesting
So
because you said it's STM basically. So I was expecting I think they use Cube, or what STM is using Cube. Yeah,
I think so. And you could totally do that. I'm 100% confident that you could, use STM's Cube software and load this model in and write the stuff for yourself. The nice thing about OpenMV is they just made it a little bit easier for you, where you can just write Python, load it in, and here you go.
How does it look?
But 100% it can work. So this is what we have. So as a reminder, here's our board. What I'm going to do, it has a SD card right here, you can see. And so what I'm going to do is when I hook this board up with USB, we'll first transfer the model onto the SD card. And then when we boot this thing up, it will then load this model from the SD card into the memory of the processor and be able to execute.
So you already have there some kind of firmware which can work with this model.
Yeah, so the cool thing about OpenMV is, first of all, you can write your firmware in Python instead of in C, which I love because it's just easy. And it converts it underneath into C, I believe, or maybe directly into binary. I'm not totally sure. And the firmware I'm actually showing right here, and it's also in my repository, so you can see. But it's very, very easy. We'll walk through it real quick. So let's first just transfer the model. So this was the model that we trained. Let's store this old one because I was obviously doing experiments before this. And there we go. So now on our SD card, on our board, we now have this model.tf lite. Okay. Now here is what we actually have for the firmware. So the firmware is pretty straightforward, but to go through it, we import the sensor. So that's the library that connects to the camera on the board. We import TensorFlow. So OpenMV provided us this TensorFlow library that can read some models and run them on the microprocessor. It can't support everything. You're not going to run ChatGPT's transformer on here. But this will work. So we load that model, reset the sensor, set the sensor to grayscale, convert it to 320 by 320 resolution, skip some frames for a couple of seconds, and then get into our main execution loop. In the execution loop, what we're going to do is we're going to take a screenshot or snapshot, which is just a picture, right? So now we have pixels. They have a lens correction, so we'll just correct the lens so that the image is kind of distorted to the correct shape. And then what we have to do next is we have to make our image look as much as possible like our training data set. So this is important. The images that we trained on, they look like this. They look like these numbers, like this, right? So if I just take a piece of paper and have a picture of me smiling and I have a 4 on it, this neural network will be useless. It's not going to recognize it. We need to show it images that are as close as reasonable to these ones. So ideally, when you're doing this for a real application, you really want to collect your data in exactly the way that you're going to be actually using it in production. So if we had a production line and we had numbers going by, you shouldn't use MNIST and then hope that it works in your production line. Ideally, you should collect hundreds of thousands of pictures from your production line, train on those, and that's where you get the best results. Didn't have the time to write 60,000 numbers for this video, so we're going to cheat a little bit. But it does still work okay. And I should mention the other thing for expectations, right? This is far from the best that a neural network can do. Like the model that we used is actually extremely simple. It's mostly just linear regressions, which we'll talk about. And you can do much, 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 much better. There are architectures that do way better. We can train with more data. We can fine tune it more, so on and so forth. So don't expect it to be perfect, but expect it to be fairly good.
So basically, the camera itself, it may not have resolution 26 or what we are using by 26, but we have to scale it down. It has maybe 260 by 260, no? Because you scaled it by 0.1 or?
Yeah, so the native resolution is 320 by 320. Okay. Is what we configured.
So you scale it down, and then you need to also maybe make it black and white or something. And
exactly.
Okay.
Yep. So it's already grayscale, but in grayscale, it still has a lot of detail and stuff like that. Okay. So scale it down. Now it's 32 by 32. I then crop it so that we're only looking at 28 by 28 pixels, exactly like our input. That's actually really important. Then I actually put a threshold on it. So to make it look even more like these pictures where we have this super nice total black behind it and some white pixels, everything below a value of 240, so 0 is black, 255 is white, just make it fully black. So this is going to make it look even more like that. The next step is to actually run the classification. So this actually gives us our result of like those 10 numbers that predict the probability of each class is here. So that'll be this model output. Yeah, so classification result, and then from that result, we get the output, which is the 10 different possible numbers. And then this is just a quick little loop that basically finds the highest number. So whatever the index of the highest number, that's the index that we predict.
So classify is the magic function which will basically tell you the results.
Exactly. So this is actually our neural network running. This is actually the neural network taking the image, the 28 by 28 pixels as an input, and then producing 10 numbers as an output that assign a probability to every class.
Okay. So now I have another question. So on the microcontroller, we already need to have some kind of, I don't know, MicroPython running on some kind of operating system, or what is already running on the board?
You know, I don't know exactly how the OpenMV guys do it.
Is it like Zephyr or I don't know?
Honestly, I actually don't know. So yeah, it is MicroPython fundamentally. I don't know under the hood how the OpenMV guys are converting this Python. You know, this is MicroPython with their own libraries into whatever C or whatever runs on the microprocessor.
Okay, so when you buy the camera, basically there is already firmware running.
Yeah.
You just write your Python application on top of it and you save it to SD card or somewhere. I don't know what you are going to do with this, but I guess you will copy it on the SD card.
Exactly. So you can run it as SD card. It's easier if we just keep it connected to USB and we can just write directly to the flash and run it directly.
Okay.
Yep. Just easier, right? Don't have to keep copying the file and over. But we totally can. We absolutely could save this to SD card and it'll run for sure.
And on your board, how is it done then on your board?
Same thing. So our board is a clone of the OpenMV. Actually, why don't we just show it?
Okay, because they are open source, you mentioned, so you can take their binaries, flash them. Okay, I understand.
Yeah, exactly. So this is our actual setup here. So we have our board. I just have it set up in a little jig so that it's pointing at my iPad. And then I'll turn on this iPad, and then I could just use my pencil to write numbers on it. And that's kind of what's actually happening here.
Okay.
So now let's see if we can first of all connect. So with that, we're connected to the OpenMV board, and then we just simply click run. And so this will transfer.
Oh, it works.
Yeah, exactly. So you click run, and it just transferred over USB and starts running it, and it shows us some result. So right now, it's literally, we see up here, actually, I should point out, up here is what the camera's actually seeing.
Okay.
So you saw in the first 2 seconds, I'll actually even just run again. For the first 2 seconds, we're not applying all of those filters, all those corrections to make the image look like the numbers we trained on. Instead, it's just seeing the grayscale image. And so you see a reflection of me in there. But then we do our thresholding and everything and just make a blank image. Now we have this. So let me get to the point where we can actually write numbers. Now, one thing is it's seeing just a few random pixels, but it's predicting 7. That is because we didn't teach the network to predict no number, right? So it's always predicting 10 possibilities. For whatever reason, this blob of pixels makes it think that the highest likelihood one is 7. And so that's what it's going to predict. If we wanted it to say, I don't see a number in this frame, then in our data set, we should have also had examples of nothing, right? It could have been noise. It could have been just black frames. It could have been whatever. We didn't do that. So it's always going to predict a number.
Yeah, I've seen
even if there is no number there.
Sometimes you train it also for background, for example, or something like this.
Yeah. Exactly. Cool. So now what I did is I turn on my iPad and I just have a black screen on it. And I see a little bit of glare. That's the pixels in the top right, but that's okay. And we can start trying to write some numbers, see what happens. So for example, let me get the number in frame.
Cool.
So I wrote down a 4. There's a 4. If we write down, let's try a 3. It's a 3.
Nice.
If we write down, whoops, let's try, I don't know, 5 maybe. That's
what
5.
if you write it somewhere in corner? Is it going to recognize it, or it...
Probably not. So that is a good question. So as soon as we deviate from our data set, in general, this is true for neural networks. They are really poor to the point of being useless and extrapolating. They are only good at interpolating. So if the number looks really similar to the numbers we've seen, it'll do well. But if we have it somewhere totally different, it's not going to work well. So for example, you wanted it in the corner. Here's a small 4 in the corner. Nope. 7. Here's another example. What happens if we rotate it, right? So if we write a 4 like this, same thing. It doesn't know what to do. So it only sees it if it's actually, in the frame exactly as we expect. And even then, not perfect, but there's a 2, for example.
Nice. Yeah. Cool.
So the question becomes, of course, okay, but the numbers are rotated sometimes, right? They are in the corner sometimes, and they are different, and there's colors and all these things. That's where this gets more and more complicated, right? So one choice, so for rotation, for example, one choice you have is just to have a very large data set where you have some rotated numbers. We can, in our computer, rotate the numbers and train it to recognize that. Or what would be better is if we train a function or a neural network that is rotation invariant, then you don't need that data. So
but you need much more input then, no?
If you just want to take this neural network and teach it to recognize, all of the many different possible rotations, yeah, you would need a huge amount of data, very, very large amount of data. But if you could make a neural network that the rotation of the input does not affect the output, then it'll just work. So these are the tricks that people start to play. Do you go and collect a crap ton of data, or do you get clever with the actual neural network function to reduce symmetries into some simpler kind of state? And this is where it'd be helpful to actually dive into how this thing works.
Okay, so what are we going to do in the next step? Are we going to have a look on the robot, or we are going to talk about how?
Yeah, so I guess that's up to you just on the time check. So the next thing I prepared is I can show more detail of how the neural network actually learns. So we can go through some more detail about what is the math, how are these gradients computed, how do we actually find the correct weights.
Let's do the robot first, and then we will talk about theory.
All right, cool, perfect. All right, so jumping to the robot.
So motivate people to see the results first, and then trying to find out how is it possible it actually works.
How is it possible? Yep. All right. So let's leave this. Here's another notebook that I made. I'll do a couple. This notebook shows us this other open source tool called Brax. And what this is, and actually I'll just go to their website just so that you can see what it is, so that people can read about it. You can see it right here. Again, it's Google, it's open source. And what this is it's a whole bunch of code that makes it really efficient to create 3-dimensional models of robots and to train this time reinforcement learning models to operate those robots.
So this is like TensorFlow for robots.
Kinda, yeah. That's a good way to look at it.
Okay.
So they have all these examples of like, here's how to teach a human to run. Here's how to teach a 4-legged, dog to walk. Here's this like 4-legged spider thing, or a robotic manipulator. And what it can basically do is the same way that we had millions of pictures as examples. We can have millions and millions and millions of simulations for these kinds of systems, again, running on GPU, so very effectively. And then from those, we kind of update the neural network to take the correct actions. So we've now shifted away from supervised learning and into reinforcement learning. So in supervised learning, we had, here's a bunch of data, 60,000 pictures. Here's a bunch of labels, 60,000 numbers. For this picture, this is the correct number. Please reproduce that. This picture, this is the number. Please reproduce so on and so on and so forth. What we're doing here is very different. What we're saying is, hey, neural network, you can take actions. Like you can raise this arm, you can lower this arm, you can rotate it, you can raise this arm, whatever. The only thing I'm going to tell you is how well you are doing at some task. So I'm just going to give you a number. If you did poorly, your number is 0. Your grade is 0. If you did well, you get a 10 or 100. Please maximize that number. And that's it. So what we're going to do in our case with, with this guy is we're basically going to simulate this in Brax. And then the number in a nutshell that we're going to reinforce is please get as far away from where you started as possible in a limited amount of time. Okay. So we're just measuring this. How far did you get?
So it may not walk like what we would expect, but it will be trying to achieve the goal. So move as fast as possible from A to B.
And what you just said is a very important point, right? That which you incent will happen, but what you incent might not be what you wanted to incent. And so that's
like walk beautifully from A to B.
How do you measure beautifully? We will touch on that because we have a little bit of that problem in this setup, and I had to do a little bit of work to beautify it, and I'll show a little bit of how that works.
Okay.
So this first notebook, I'm just going to run through it just to kind of show the basics and show kind of how this works. This comes directly from Brax. So I did no work here at all. This notebook is available directly from them. It's meant to run in Colab. You can run it in Colab, reproduce the results. Really cool. And I also have a copy of it in my repository for anybody who wants it. And I won't run it because the training on these things takes a few minutes. I think this one's set up to run for about 7 to 10 minutes, and I won't make you wait. But the results are already here. So
yeah, okay. So you already pre-run everything.
Correct.
Okay.
Yep. Cool. So just like before, first thing is import a whole bunch of tools. So different Python tools, Brax itself, Flax, which is like a neural network training thing. And then our actual reinforcement learning algorithm that we're going to use is going to be PPO, proximal policy optimization, which we can talk on the theory a little bit later. But the basic thing to understand with the reinforcement learning is we still have a neural network. It still takes some inputs and produces some numbers and output. But the two things that are changing are, number one, the inputs that it's taking in this case are like what is the current state of the robot? So where exactly are all the arms and legs right now? How fast is the robot moving right now? What is the angular rotation of the robot right now? So you can almost think of it as like if you actually built a real robot and you instrumented it to have measuring all the joint angles, measuring the current position and speed with or acceleration with the IMU, so on and so forth. Those could be your inputs. Yeah, in an even more practical setting, maybe you have a camera that's like looking at the ground, trying to detect obstacles. That could also be an input. So all of those kinds of sensor data about the world are coming into the neural network. And what the network is doing is it's choosing an action, which means it has some possible levers to pull, like, literally like move this joint or move this joint or so on and so forth. And it's going to choose what to do for all of those possible actions. Mm-hmm. And then, of course, the second difference is that we're not just going to give it a million examples and say, always do this in this case. That doesn't really work in reinforcement learning. The amount of possible configurations is tremendous. And so it would be very, very difficult, maybe not impossible, but very difficult to assemble that kind of data set. So instead, it's going to figure it out with this proximal policy optimization algorithm that updates the neural network configuration in such a way as to try to maximize that reward. How far away did you get from the start?
But this is interesting because there are suddenly two places where this software can make the updates. It can update the robot, like the positions of the arms and everything, and it can update the weights. So how does it? I think that's complicated.
Yeah. Yeah, so it helps to actually completely separate those two things that you just said. So there's how do we update the weights, and then how do we update the robot? And we have some slides on this in the theory section, so we can dive into it deeper. But in a basic sense, the actual training algorithm and all the Python you see here is never updating the robot. Mm-hmm. The only thing it's doing is it's changing the weights. Mm-hmm. So actually, you know what? This is actually a relatively simple example. So this isn't what we're going to do here, but there's another way to train reinforcement learning agents called neuroevolution. And in a nutshell, the most basic version of how it works is try random numbers for all the weights for the configuration of the neural. Now you have a neural network, which is the policy. And this policy is what should the robot do given a certain state. So you set up some random weights, and then you say, hey, policy, go play. And you put it into the environment, and you just let it run for 10 seconds, right? And it's random, so it's going to do random things. It's going to wiggle its arms and twitch and whatever else, right? And then you stop, and then you just measure how far did you get. Now, you could do that a million different times with a million different weights, and presumably you'll get lucky. Like one of those weights got a little bit further than the rest of them. Okay, let's just take that configuration, start it from scratch, make small modifications to those weights a million times, let it play again for a million times, and choose the best one out of that population, and over and over and over again. So in this way, it's kind of a really, really dumb, simple, it's not an efficient algorithm, but it is possible to basically just randomly try weights, pick the best one, restart there, randomly perturb the weights, pick the best one, randomly perturb, pick the best one, and you will actually find a configuration for the neural network that gets it moving somehow in the correct direction. So that's kind of the key distinction here, right? Like on the one hand, we have this algorithm that is somehow choosing the weights. And then to determine if the weights are good, we freeze them. We don't change them.
Okay,
we put them in the simulator and we say, go play.
Mm-hmm. So you decide on these weights, on the model, and then you run number of simulations of your robot on this fixed model, and then you figure out if the model is okay or not. And then you change the model, and then you again rerun the simulations of the robot doing something, and then you say if it's, but you know, there are these two places, right? Like you don't know if you are doing wrong here or here, if the weights are wrong or if the movements are wrong.
Yeah, well, but the weights directly control the movements. So
okay.
As long as your simulation is correct, let's assume that the simulation is written, there's no bugs or anything like that. The weights in the model are exactly, well, the weights in the model plus whatever the current state of the simulation is what determines the movements.
Okay.
So like whether the robot is waving its arm randomly without purpose,
I understand.
or if it's actually doing like a smart motion is entirely determined by the weights of the neural network plus the current state of the robot.
So basically, we know that this movement is better based on the weights which are already there, or something.
Yeah.
Like
So
this.
like,
okay,
if the robot managed to travel further, it must mean that the movements are better, which must mean that the weights are better. So keep those weights.
Okay.
Then change them, and if the robot got further, then those weights are better. If the robot did not get further, then those weights are worse. You keep the old ones. That's basically it.
Okay, I understand.
Okay. All right, so we've imported Brax. Brax has a whole bunch of different simulations that you can play with. They're all super fun to watch. In this case, we're going to play with the ant. So it's this four-legged robot thing here. And it has a whole bunch of ways to approximate physics, generalized coordinates, positional coordinates, spring coordinates. Not super important, but we'll use positional, good balance of accuracy and speed. But this is basically the physics engine. Then what we're going to do is we're going to create the environment. So we literally have this open plane in all directions, and we have this little body here, and then we have a couple legs, and the legs can, you know, rotate at the hip, go up and down, and then rotate the kind of ankle kind of thing. We then compile that whole thing. So JIT, just-in-time compiler, it's exactly just like, well, I guess you don't have just-in-time compilers in microprocessors, but in software, just-in-time compilers are pretty common. Again, just to make it run fast on GPU. And then we can just make an HTML page that renders this thing. So this is basically just some HTML that shows the simulation. So for right now, this is our initial point. We just have this robot. It's standing somewhere on a plane at position 0, 0. Nothing's happening. Then, and Brax has a lot of nice like explanations and tutorials and stuff that people can read. That's fantastic. The next thing we're going to do is we're going to configure the training function. So Brax provides us with some examples that where they have picked good algorithms and good configurations for those algorithms called hyperparameters that they have proved already work. So you don't have to search for them yourself. So in a real application, you would have to choose what reinforcement learning algorithm you want to use. You would have to choose all the different hyperparameters of that algorithm. So there's knobs on the algorithm itself of how to actually train the neural network, and searching for those is also difficult. But Brax already did that. For the ant environment, they chose this one. So this is going to run 50 million time steps and do, a whole bunch of stuff in terms of configuring how it's learning, but we can just take it for granted. And then we'll have a progress bar. So basically this progress kind of updates as we train, and then we actually run the training function. And so here what we're seeing is, again, this is pre-run. It just takes 4 minutes to run and 49 seconds to compile. So instead of doing that, you could just trust me that I already did it. And you basically see that an episode is just one game, so to speak. A lot of times people think of reinforcement learning in terms of games. And in this case, we have a game where the robot tries to get as far away as possible. So an episode is just a single game where you get to the end and you either win or lose, or in this case, you just get a score.
So in this episode, do you use only one model?
Yes.
Okay.
Yeah. So this particular plot probably averages over many, many episodes because this is happening while we're training. But in a simple sense, yeah, we can just run a single game. And we actually have an example of that lower down. Just run a single game, single model, single robot, single simulation, let it play. And we'll look at that in a minute. These are probably averages. And so you can see, of course, at the first part of the learning, nothing's happening. It's doing random movements and it's staying in the middle and nothing useful is happening. Over time, it gets further and further and further away from the center. And even after 50 million examples, it still seems to be kind of getting better. So maybe you could even find a better and better way to move away from the center. That's what we're seeing here. But it's cool. I mean, you can do 50 million physics simulations for this entire ant in just 4 minutes. I mean, that is wild. That kind of thing is amazing.
Can we also see how it is moving?
Oh, yeah.
And doing nothing?
Yeah. We can pull up an example of what happens in random. That won't be too hard.
Okay.
But let me just get through this so we can save the model. That's if you want to load it later and stuff like that. That's fine. And then finally, this is the actual result.
Okay.
So in this case, this is a well-trained model.
Okay.
So in this case, it's going to be a good robot that actually learned how to walk. So we're going to monitor it. I'm going to freeze the angle here. And then this is what it learned how to do.
It's basically only using 2 legs.
Yeah, so one important thing here, the reward was actually not as simple as I stated. It's not just how far away did you get. In this model, they also added a punishment for how much energy you use.
Okay.
So you want to be as efficient as possible while doing this. And so, of course, it figured out the most efficient way is to use only 2 legs. So you're kind of just hitting on the back end to not fall over.
Stabilize the... Yeah.
That's it. And you can kind of see that in this simulation, this robot has enough power to kind of leap almost. And so it really kind of takes off and kind of jumps. It's almost floating, yeah. I mean, it's a real physics, so it has to have friction, it has to actually push, all those things. But because we gave it a lot of power in the simulation, it can kind of jump off, right? Yeah, so if we wanted to see what happens when we do it random, what would be the best way? Let's try to just skip this part.
So basically this is finished, correct? Then after the training, you have the final model, which we will then upload to our robot, which you have on your table.
Correct.
But now we would like to see how it is learning.
Exactly.
Okay.
Yeah. So in this example, this is just, so another thing is that this is a 4-legged robot. Ours is 6.
Okay.
So we'll have to make those changes as well, and I'll show that in a minute. But it's kind of fun to see how this thing learns. So just turning off learning, let's make it learn for 1 time step. So basically something useless.
It's finished.
Yep. Yeah, so that finished up. And then now it's going to do the visualization. It actually ran for a little longer than I thought for training. So maybe it's the actual iteration loop for training that took a little longer than I thought, but that's okay. This will take a minute to actually produce that video of it playing.
If it's
But once
taking
it's done,
too
we can
long,
kind of see.
I will speed up this, or I can,
Oh, perfect. Perfect.
or possibly we can just load the firmware to the robot or something.
Yeah. So let's actually, while we wait for this, I'll show the next part, which is how we adapt this to our actual six-legged robot, and we'll
Okay.
jump to that part. So hexbot, here it is. There you go. So that's what happens when it learns almost not at all. So it learned for just one time step, not a whole lot, and it just barely gets a little bit of an idea how to get away from the center, but not really doing a good job. Whereas last time we saw it like skipping along in the right direction very efficiently, very quickly. So for the sake of time, maybe we shouldn't go to every single time step, but if you just change that one number, like how long you give it to train, you'll see it get better and better and better. So in maybe 100,000 time steps, it'll kind of like squiggle in the right direction, but not very quickly. Then it'll start to learn to run, and then eventually it learns to like hop really nicely, like we saw in earlier.
Okay, so let's upload it.
Let's do it. So before we do that, before we upload it, we have to change it to work with 6 legs.
Okay. Yeah.
So I've already done that, and that's all taken care of.
How did you do it?
So just to show that real quick, let's make this full screen. All right, so this is the same exact notebook, but this time I called it Hexapod because now we have 6 legs. And I made some changes. And so you'll see it being very similar, but there will be some changes that I made. The first change is I made an actual custom model to represent the robot. So underneath Brax, they run on this physics simulator called Mujoku, which I think Google acquired some years ago. And it basically uses these XML files to define what the robot will be.
Okay, so, I was actually thinking about how does it know what are the angles what you can use, or what is the speed, what is the weight, or I don't know.
Exactly. Yeah. So this is actually everything that tells our robot what the robot is. Right. So we literally have like, here's your front left leg, here's your middle left leg, here's your middle right leg, front right leg, back right leg. And then here are all of the motors that you have available. So hip 1, ankle 1, hip 2, ankle 2, blah, 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 blah.
Okay.
So I make this, so the ant that I showed earlier has an equivalent file. In my case, I'm just overriding it with my own that has 6 legs. The other thing I did is I pulled out the actual reward function. So to show how we are actually giving a score to this thing. And there's a few things to highlight here. So first reward is just velocity right here, right? So if we're going fast in direction 0, so in the X direction, that's a good reward. The second thing I did for my case, and this is a part of the make it walk nicer, is I made it not get any extra reward if it goes above a certain speed. So for my case, my motors don't have the strength to leap and bound off my desk. So instead of letting it train to go as fast as possible, I just said, hey, once you get to a good speed, good enough.
Okay.
At that point, I just want you to be as efficient as possible. So that's what this clip does. This clip, it literally says, if the function reaches above a certain number, stop at that number.
It's clipping.
There's some clipping, exactly like that. There's some things here for if the robot somehow falls to the floor in the simulation or takes off or something, like some glitch in the physics system. We just want to throw that data point out. So this kind of thing determines that. And then the other thing is this control cost weight. So basically, we can take we can square all of our actions. So the action is literally for each motor, how much power do you send to each motor? And then sum them. So just sum the squares of the actions. And that gives you a total amount of kind of energy or total amount of force that you've applied. And so what we're going to do is we're going to subtract that from the reward so that we kind of minimize the amount of power we need to send to every motor. So then this is the final reward, right? So in this case, forward reward is just, are you moving forward in the correct direction, and clip. Healthy is just, are you still alive, right? Did you fall off the page somewhere somehow? The control cost is what we kind of just said about minimize the amount to which you have to drive every motor. And then this contact cost must be a legacy thing in their code. It's just 0. So they must have been doing something to reward it touching the floor or something like that. But it's just 0. So you can delete it. It's not doing anything.
Okay.
But that's the main thing. So this is what we're telling the robot, good job or bad job. All right. So we load the environment. Now we have a 6-legged robot instead of 4, but same exact thing as before. We set up our training loop. In my case, yeah, so same kind of thing. I used exactly the same parameters, so I didn't change anything. You know, it works well enough. Run this training loop, so 46 seconds to compile.
Minus 2000.
Yeah. Oh, so one thing that I changed is that because I only allow it a certain max speed, it can't gain as much from going fast. So its overall reward is now lower than the previous one. So it starts with minus 2000, which basically it's spending a lot of energy moving its arms, but it's not going anywhere.
Yeah, okay.
And so that's why
it's failing, basically.
It's failing, yeah. And then over time, it learns, you know, at some point, the amount of energy it's spending and how much it's moving in our arbitrary choices of how important each function is become equal. And then eventually it's moving a lot and not spending a lot of energy and the number goes up. It's not actually that important what the absolute numbers are for the reward, unless you specifically know what they are. It's just important that they're going up and to the right. Okay, and then we save the model, that's fine. And then we simulate it. So just to show you what it should look like, reset, and then, let me pause it to grab it. And let's not rotate, let's play. So this is what it learned how to do. So it's kind of walking in that direction. In this time, it's using all 4 legs. And you'll see, because I made it move slowly, it's not jumping, right? So it's just neatly going step at a time. It's taking cautious little steps because it's trying to minimize how much each thing does.
But it's moving sideways. That's interesting.
Yeah, so when I set this up, inadvertently, I put it in the X direction this way. Which is just along this edge. Now, here's something really interesting. So I don't have time to run this now, but I then switched it to move in the Y direction because I wanted it to move forward. And what it learned how to do is to turn around and go sideways in the correct direction. So somehow, this is the most efficient orientation for this robot to walk.
That's why crap is moving sideways. I don't know if it's, I don't know. I'm just...
Maybe. Yeah, maybe. Because you can also kind of think, what this reminded me of when I saw this is, it's kind of like it has a tail and a head. So, because it kind of, you can see the, whoops, let's not get away from it. No, there you are. You can kind of see it's wiggling the tail in the back to kind of keep balance and the head to keep balance. And then it's using the 4 legs to walk. So I didn't intend this. I was hoping for it to actually use all 6 legs to walk, but this was more efficient. And so it kind of uses the front and back leg almost like a head and a tail to keep balance almost, and then the other 4 legs to actually make progress the way we would expect.
Interesting. It's really interesting.
Yeah, for sure. Okay, so finally with this, now all I'm doing is I'm recording this specific playthrough where it's doing these exact motions, and I'm just going to replay them with my robot.
Okay.
So ideally, what we'd really want to do is ideally we'd have 50 million of my robots. They would actually play in the real world. They would figure out how to walk in the real world using their own sensors in their own environment and then do that. And people do that, but it's harder than this, right? So it's an active area of research. How do you avoid needing 50 million robots to get something like this to work? So we didn't do that.
But this is interesting because, I'm sorry for interrupting, but I was actually thinking how you are going to put this model on your robot, but as you say, it's not really necessary. You just need to upload these movements and repeat them. Exactly.
Okay. Exactly. So I mean, it in some cases it's necessary to actually run the model on the robot to actually respond to your environment. In which case your model has to be a lot more accurate. Like you have to have the same measures, the same torques, the same angles, the same sensors available, all that stuff. I just bought a $100 robot off Amazon, right? So I didn't go through that effort. That would be the next step, is to make the model be really, really close to the actual robot, trained in exactly the same way, run the model on the robot and have it dynamically respond to the environment. And that's when you see people doing demonstrations of like the Boston Dynamics robots walking and stuff, like you can kick them and they respond. That's how they're actually running a model. So we won't do that because it's quite a bit more complicated. But you can still teach it to walk forward, teach it to walk backward, teach it to walk right and left, hook it up to a joystick, and just replay the correct direction, and then you can have it walking with this. So let's get to it. So on this robot, what we have here is it's just 18 servos hooked up to some batteries basically, and a Raspberry Pi. So in here, you'll recognize this is a Raspberry Pi sitting in there that I have connected to the network. Hopefully still connected. It's been a little while. And then what we'll do is we'll see if we are actually still connected. We are. Let me make this screen bigger so that you can see what's happening. Okay. All right. So basically, we have this walk function. Let me do this. So we have this walk function, a little bit of code here. This is actually just raw Python because Raspberry Pi can run Python. And it basically just takes these list of numbers. These are positions, but what we're actually taking is the rotations. These are the rotations, the quaternion for every single motor on the robot, and telling it to go to a certain position. Let's do that. And so all we're doing is playing it back. So we just iterate through those, and we set the servos to the correct angle based on those rotations, and that's it.
How did you get this rotation from the simulation?
Yeah, so in the simulation, what I did is, it's this function down here. So we have this rollout list. In reinforcement learning speak, a rollout is a single example of the game being played. So this one recording is a rollout. The way we got the rollout is, here we have the environment that we created. We compile it to make it fast, give it some random number to start with, reset the environment so we start at 0, iterate for 1,000 time steps, so 1,000 steps in the simulation. Then this will basically add the current state of the robot to this rollout list. Then it will do an inference. So this is basically, hey, neural network, please tell us what action we should take. This will update the state. So given that action, hey, environment, please tell us where our robot is now and where all the legs are now. And then we just add the actions to this list to keep track of them. So that's how we're making this rollout. We're basically saying, let's restart the environment. Let's take our actual neural network that's going to make these choices, and let's just record what it does and have the environment simulate what happens.
So record the movement of all the legs, and they are in these position and rotation.
Exactly. Yeah.
Or basically rotation. Position is also like position in this 3D environment which is there, but that's not important for us, correct?
Correct. Yes.
It's not position of the servos or legs or something.
I actually think it is.
Okay.
I think it is the position of the actual servos, but or maybe not. Let me see. No, it is. Yeah, it is the actual position of all the servos and kind of global coordinates. That's not what we're using. We're using the rotations, which is, it's really a set of quaternions, but I can reduce it to just a single angle. What should the angle be? In a nutshell. And so and then the other thing I did is I rescaled all of these things to make sense for my robots, right? Because 0 degrees means something different for this one versus my robot. So I just took all that into account with some constants. And that's it. All right, so let's actually run this.
So it should be moving one direction only and repeating what we see in the simulation.
And so obviously you'll see that there's differences between the simulation and real life. Like my desk is pretty slippery, so it's going to slide around a bit more. In the simulation, it's actually responding to its environment. So it's kind of like, if I rotate it too much this way, the model is smart enough to correct that. But in my thing, it's just doing a playback. So if it rotates incorrectly, it's not going to be able to correct it. It's just going to keep going straight, like whatever direction it wants. So it's not perfect.
I'm curious.
But that's okay. We now have this. Let's actually point at the bot. So, oops, wrong place. Let's point there. That's the robot. And then let's give it power. Now it stands. And then... Oh, I had the leg fall in my cup holder. There we go.
Cool.
Okay, go back. And the funniest part was when my dog saw this, he freaked out. What are you doing, man?
This is cool.
All right, and kill switch. That's it.
Super cool. Okay, and now we are going to learn a little bit more how it is actually really working and learning.
Yeah, let's do it. So what I'll do is we have presentation, which comes with another notebook. In this notebook, we're going to play with a much simpler data set to kind of really illuminate how these networks work.
Mm-hmm.
And so we'll go side by side with training a really, really simple model on a really simple data set and show a little bit of stuff in the presentation to kind of illuminate how it really works.
Okay, I'm curious.
So the main point that I want to land at first is just how similar all of this is to simply fitting a line to some data points. So just like you remember at school, you'd have, a whole bunch of data points and some plot, there's some noise on them, and you do a regression, you find a line, y equals mx plus b, and there's some way to make that line match really closely to that data set as close as possible, and you can calculate the r squared value. And if r squared is 1, you have perfect result. If it's less, not so perfect. So what I'm going to show is how to use a neural network to do exactly that. And it'll demonstrate what's really happening, at least in the supervised learning case, just to give you really intuition of what's happening with these networks.
So we are going to use some kind of simple function. I see what it's simple. Not linear function, but maybe something else.
Yeah. So we can do linear first, and then we'll do sinusoid to kind of exploit some of these.
So we will have some data into the plot, and we will try to find a line which is closest to all the points.
Exactly.
Okay.
Exactly. So to start, let's actually clear everything. Oh, maybe there isn't a clear. Oh, that's fine. That's okay. Let's just run this whole thing. Anyway, okay. So same thing as before in the handwriting data set, right? So we import our libraries, TensorFlow, Matplotlib, NumPy. We'll make sure that we actually have a GPU. Mm-hmm. In this case, GPU is really overkill. You really don't need it, but whatever. We have it, so why not? The next thing we'll do is we'll create our data set. So instead of handwriting, which is kind of a little bit more complicated, we have all these pixels and labels and stuff like that, we're going to do a regression problem rather than a classification problem. So we're going to take a number and predict a number rather than take a matrix and predict a set of numbers. And so in this case, let's just start with something really simple, a line, right? Y equals mx plus b, 0.2 slope, 0.3 intercept. And what we'll do, let's actually just start with even 2 data points. We'll get 2 data points and just make a line, a data point is 0, a data point at 1. That'll be this function. So this creates our list of x values. It'll just be 0 and 1 in this case, pretty much. This will be our list of y values. So at 0, it'll just be the intercept, 0.3. At 1, it'll be 0.2 times 1 plus the intercept, so 0.5. Mm-hmm. Right?
And all of them should be on the 0.2 multiplied by x plus 0.3 because there is no randomness.
Yeah. So okay. I will later introduce noise, but for right now, I have it commented out.
Okay.
So we make our training set, just two training samples. That's it. Mm-hmm. No more. We don't need more for now. And then 100 test samples. So this will be 100 points across that line. Mm-hmm. Let's make the simplest neural network possible. So for now, ignore everything here in green. It's commented out. So all we have is this flatten layer, which actually might not have even been necessary here. It's basically just converting whatever the input is into a single vector of numbers. But in this case, we're only inputting one number. So I can probably actually delete it. And then just what's called a dense layer. So in neural networks, they are a composition of functions. So each of these layers is a function. So flatten is a function that does something, dense is a function that does something, dropout is a function that does something, ReLU is a function that does something. Now, dense is the simplest one. And so let's talk about a little bit about what that function is.
I have a question. Sure. So is this like, when I was doing the other video, we mentioned filters applying on pictures, like finding edges, for example, or something like this. So this is basically, these functions are these kind of filters which will help us to see better.
Absolutely. Okay. So I actually have an example of that in my slides. But yeah, what you must have been looking at is convolutional filters, where the idea is instead of taking all the pixels and just doing a raw operation on all the pixels, you take a small 3x3 kernel and you convolve it around the image. And so you can, like, you've maybe even written an edge detector like this before, where you can do like you can actually create your own little 3x3 filter, like a Sobel edge detector. It's just a matrix that like takes a derivative in both dimensions. And if you convolve it, you'll get a really nice edge detector, right? But in your case, for that video, you must have been learning those filters. So you must have been finding all these different filters that extract nice features like edges or, you know, textures and stuff like that. So yeah, so in that case, that was a convolutional layer that had some number of filters that take the input and produce some new input after those filters. In our case, we're going to go much simpler than that, much simpler even than the convolution. As a reminder, what we're doing here is supervised learning. So again, bunch of inputs, bunch of labels. From that input, please predict this label, and we hope it generalizes to previously unseen inputs. Again, you know, before we show this with numbers, so we have a bunch of zeros, ones, whatever, and we're just taking this image and converting to a 5. In this case, we're doing regression, so we're just going to convert a single number into a single other number, an x into a y. That's it. Now, these networks, the thing that we saw about them is that they are functions, right? So they take some input, they produce some output, and there's a few things that are important about them. So they must be configurable. So there must be some weights that we can tune on them to change what the function does. So in the function y equals mx plus b, m and b will be our configurables. And that's what we can tune to fit the line.
That's the weight?
That's the weights, exactly. They also must be differentiable, or mostly differentiable. And the reason is that we want to roll that ball down the hill. So in order to know how to update the weights, we want to take the derivative of the total error of that neural network on that example in the direction of the weights or along the weights. And that will tell us which way should we push the weights to reduce the error.
So differentiable, it means we need to be able to kind of get closer to what we want by adjusting this.
Yeah. So you can, the strict meaning of differentiable means that we can perform the calculus operation of taking a derivative. So if you remember from calculus, like integrals and derivatives help us find the slope.
Okay, I understand.
So exactly. So that's all we mean is it's for this kind of paradigm, it's really helpful for us to be able to take a derivative of this function so that we can measure the slope of the mountain we're standing on, not just the height of the mountain.
Okay, I understand what is it now. I didn't know that that's the English word for this.
Yeah. Differentiable just means you can take derivatives. And then the last thing is that they need to be what is in theory thought of as a universal approximator. So for example, what I mean is that suppose you have a really simple function that is just y equals b, right? So it's just y is equal to some constant, right? Well, if you have that function, it can only approximate a horizontal line at some height, right? So if your data set is just a horizontal line at some height, great. But if your data set is even tilted or has a curve or a sinusoid, you will never find a correct parameter b to fit that. And what that means is that the set of all functions that are just y equals b for all the possible values of b do not constitute a universal approximator in the space of all functions that exist. So the simplest example of functions that approximate everything, you also might remember from calculus, or actually even from electrical engineering, the sinusoids, right? The Fourier transform works because sines and cosines, when added together, can represent any other function, like a square wave or, you know, an impulse or whatever else, right? From calculus, you might also remember that polynomials are universal approximators because you can take the Taylor series and you can approximate any other function with just a lot of polynomials. So this is the other important property of neural networks, is that they have sufficient flexibility to eventually represent any kind of function. And that is what gives you hope that you will find the correct function for your data set and your application. Okay, so and there are many architectures. So architect is just what is the set of functions. So you mentioned convolutions. This up here is an example of such an architecture where you're taking an image, it's a matrix, you're taking these 3x3, or maybe they're different size kernels, and you're convolving them throughout the image. That gives you a new image, right? Then you subsample them. So you take those and you average every neighboring pixel, and then you run another convolution, and then you subsample and you run another convolution.
But that's not really, that's not the network. That's not the neural network. This is just adjusting the, or applying some kind of processes to prepare input for the network, or?
In this case, it actually is the neural network.
Okay.
So so we won't be diving into convolutions in this example, but in general, when you train, like if I was to train a better handwriting model, I would use convolutions. And in the convolutional network, the configuration you are changing is the actual kernels. So that 3x3 matrix that's actually converting an image into some filtered image, you're actually changing that and making it from scratch. Now, there are tricks. So for example, if you already have a very, very useful neural network, one that has been trained to recognize dogs and cats and cars and whatever, it already learned something really useful. It already has a lot of these filters that do useful things. So a lot of times what deep learning practitioners can do is they can take an existing network that has already been trained to recognize cars and dogs and cats, and they'll use the front part of it, so all of the filters, and they won't change them. And they'll cut off the back end that actually makes the final classification prediction, attach their own, and tune that. So now you're using somebody else's filters that they learned over, millions and millions of examples of pictures, and you're fine-tuning the actual end of the network to use those filters to apply to your problem. That's kind of a shortcut to avoid the effort of training the whole network yourself. But if we were to do handwriting with convolutions, the easiest way to do it is to actually learn each convolution kernel.
I understand now. Okay, so basically you can have theoretically this neural network even in several blocks which are connected in series, if you would find it useful, or you can train everything all in once.
Exactly. Now, those blocks that you're mentioning, those are, so you're thinking of them as like individual entire networks.
Yeah.
You could definitely do that. But the networks themselves are made out of layers. So in this case, we have, one convolution, then we have another layer that averages the image for neighboring pixels, then we have another convolution, then another averaging, then the flatten operation, which turns into a single vector instead of an image, and then dense networks, which we'll talk about a little bit more. Those different layers are the depth of the neural network. So when you hear deep learning or deep machine learning or whatever, the deep is how many layers of depth you have in these networks. And the basic principle of a deep learning engineer is it's not working well, add more layers. And the theory there actually kind of makes sense, right? Because the more layers you add, the bigger your possible set of functions you can cover. So you're making it a better and better universal approximator as you add depth.
If you know what you are doing.
Cases. Yeah, of course, the problem is the deeper they are, the harder they are to train. And so that's where it falls apart. So you play this balance of like, make it deeper, make it bigger until it's like either going way too slowly or just not working at all. And then you're like, crap, let me back up and like be smart about how I make it bigger.
Okay, so just make it clear, all these are called layers. Every single, okay.
Yeah, so the three pictures here, this picture, and this picture are different architectures. Within each architecture, there are layers that work in different ways. So in convolution, we have these kernels. In a deep network, not deep, in a fully connected network, so the most basic type of neural network that people studied in the 80s and 90s are these fully connected networks. And they have a very simple operation. All they basically do is they take a set of numbers. So for our case, we can even just reduce it to one number. So one of these neurons that we have here, just pretend that there's not many of them, that there's just one right here, just a float. And then you apply a linear operation to it. Y equals mx plus b. That's it. So you can actually see down here. Maybe it's a little hard to see. I can zoom in a little bit. Let's go a little bigger. You can see right here, the formula that we're applying, so x0 is just a number, 12, right? The formula we're applying here is, y, the output, x1 is going to be wx plus b. So just a just a linear function. That's it. And we put that into the second layer. Then this sigma represents an activation function, which we'll talk about a little bit later. And then you just repeat. Again, apply another linear function, activation function, linear function, activation function, and stack them. And we'll talk about the importance of activation functions soon. So for a single number, that's it. You can just have a linear function, activation function, linear function, activation function, linear function, activation function. Those are the layers of your network, and you can train that network. Now, what you're seeing here is it's useful to have many, many, many linear functions next to each other. So in this case, we have these arrows, even just from one number, can go to this one, which has its own slope, its own intercept. This one, which has its own slope, its own intercept. This one has its own slope, own intercept. So we take one number and we apply it to 10 different linear functions. And then each of them goes to the activation function, and then we repeat. So here, this output goes to each of these inputs. This output goes to each of these inputs. That's what makes it fully connected. So you're making a single input, turning it into 10 linear functions that have an output, and then passing each output to another 10 linear functions, and then they're kind of averaging them up and then sending them to the end, so on, so on, so forth, until in the end, in our case, we're going to have just a single output. If you were doing classification, you could have 10 outputs, just like we did in the handwriting example.
But for more complex brains, instead of linear function, you use, for example, sinus because you can cover more space.
Yeah, so this is going to be a critical point that we'll cover in a minute. But basically, the problem with linear functions is a linear function of a linear function is another linear function. So if you try to just stack linear functions, you're not going to get anywhere. You're only going to get a linear regressor. That's where the activation function comes in. So the activation function introduces a non-linearity. And so then, and they can be really simple. Like the simplest activation function that people use nowadays, in a lot of cases, is called the ReLU. It's just a rectifier. So just like from electronics, you have a rectifier where if your voltage is positive, you return the same voltage. But if it's negative, you clip it to 0. That's it. That's the simplest activation function. Just if the number is positive, it's the identity function. If the number is negative, the number is 0.
Oh, okay.
Really simple. And the nice thing about it is it's very fast to compute. The gradient is always really obvious, so on and so on and so forth. But it's enough combined with linear functions to actually make a universal approximator. And in our handwriting example, that's actually what we did. The only thing we used was linear functions and rectifiers. And we got that to learn handwriting.
And who decides on this, what kind of brain we are going to use?
You do. As the engineer, that's what you do.
And that's the know-how?
Yeah, so that's the kind of like, start with some examples, start with some problems that people have solved that are similar, many examples online. And then when you start getting deeper and deeper, you start making your own changes, your own proposals, depending on what the problem is that you're solving. And then if you're a researcher, you're proposing entirely new layers, entirely new functions to use in this whole stack up.
Okay, I understand.
But that's what we do. So in our choice, we will actually play with what layers we can use and what the results are.
So for example, because I know you are designing this algorithm for PCB layout, for example, so this is exactly what you have to design by yourself.
Exactly. Whoops. Drop water. Exactly. So we frame the problem of PCB design. In our case, we try to, we don't follow the principle of learning from humans. We think that that's a mistake. First of all, there's not a lot of data. And second of all, the good designs are not online, and there's not enough of them. So what we want to do instead with our company is do a reinforcement learning, but instead of having a robot walk and get as far away as possible, we're going to have our neural network design a circuit board while optimizing manufacturability, cost, and minimizing effects from electromagnetics and thermodynamics. So if you can make it cheap, lower layer counts, cheap to manufacture, reliable to manufacture, and eliminate crosstalk and reduce or support high currents and stuff like that, great. You've got a good design, good job, robot. You walked in the correct direction. If you can't, then you didn't. So that's what we're trying to do, is we're trying to make these things in combination with regular algorithms, make these neural networks that help choose the direction of our algorithms and choose the direction of how the PCB will be made to then optimize all of the things that a typical engineer cares about, like, you know, cost and size and physics.
Okay, I'm curious. I'm waiting.
We'll get there. Okay, so dense nets. So as I kind of mentioned, the first part is this just straight up linear function, y equals mx plus b, for each one of these. And since we have many of them in parallel, we're adding them together. And then if we have depths, we're composing those functions. And then we have these activation functions. Another simple activation function is tang, just the hyperbolic tangent. You know, it has that kind of nice nonlinear shape. Another is the sigmoid, which is kind of an exponential that looks really similar to the hyperbolic tangent.
So it means you have like linear function and then corner and then continue with some other linear function or something like that?
Yeah.
Okay.
That's a really good way to look at it with the ReLU. Cool. So these are the different activation functions like we already mentioned. So, you know, so obviously, as we talked about, a linear function of a linear function is just another linear function, right? Pretty easy to calculate that yourself. It's just a different W and a different B, right? Different way, different intercept, different slope. And so that's why we add these activation functions, because then when you start composing them, they are not trivial like that. And the one that you'll see me use, so ReLU is the one that we used in the handwriting one. We can also use the leaky ReLU, which learns a little bit better, because it basically is similar to a rectifier, but instead of going to 0 below some number, it goes to some slope near 0. So instead of just being 0, it goes like 0.1 slope and slowly down. And that helps because it's, when you have a ReLU that's at 0, your gradient is also 0. So you don't know what direction to take the weight. If you have a little bit of a slope, it helps the gradient know which direction to go. But I didn't check if OpenMV supports leaky ReLU, so I just used ReLU because they definitely support the ReLU. They might, I just don't know for sure. Okay, cool. And then what is the kind of process? And I'll show this in the notebook once we kind of get through this. So this is the main loop that we kind of do. So we have our inputs, you know, a picture or a number or whatever. We have our neural network, which has some weights and configurations. It predicts an output, so y prime in this case. This is a classification task, it's 3 numbers. So it's very likely to be the first class, not likely to be the second class, not likely to be the third class. Then we have our ground truth. So this label showed us the first class was actually correct. So we should have predicted a 1 for that class, 0 for the other ones. We feed that into the loss function. So that's measuring how different is this vector to this vector. In this case, they're pretty close, but there's still a little bit of difference. You want to push that first number to 1 and these 2 numbers to 0. Now with that, this loss function is actually a full analytic function that includes your entire neural network and the error, and you can take derivatives of it. And we'll get into that in a second. But basically, we then literally take d loss, d weight. So like, in what direction do we need to move a specific weight in this neural network to make this loss smaller? And we do that for all the weights. And that's this gradient. So that's actually the d loss, d weight. And then with that, we just take a step in that direction, right? So the new weight that we set is just the old weight, plus or minus whatever, the gradient times some constant, which is called the learning rate. So how fast do you want to roll the ball down the hill is the learning rate. And that's it. So you now have a new you have a new configuration for that neural network, new weights. You try again. Now you get a different prediction. You get a different sample, different ground truth. You measure the loss again. You take the derivative again. You update the weights in the direction which minimizes the loss. And you loop, 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 loop.
So it means that our brain should be basically this exact same function what we use to generate the numbers? Yeah.
Okay. Yeah. So we'll make this, we'll make our brain here a little bit simpler at first than what we used for handwriting. But yeah, they're very, very, very similar. So before we go into any more theory, let's actually play this out for a little bit. So let's start. So we already showed that we have some basic data points. Let's start with the simplest possible brain. So we're just going to take a single neuron. That's it. And it's just going to take an x0 in. It's going to apply w1 x0 plus b, so just linear. I'm not even going to give it an activation function, no activation function. And then we're going to go straight to the output. And there's only going to be one neuron. So really, really, really simple.
Okay, how do you decide on initial values of this weight?
So we don't, actually. In this case, what this 1 represents is not the initial value. What that 1 represents is that there's 1 neuron.
Okay.
So inside of this dense layer, there is 1 neuron. That neuron has 2 configurations: the weight, and that is the slope in front of the x, W1, and what's called the bias, which is this B. So the slope is the weight in this case, and the B, the intercept, is the bias. And it's just because the bias is independent of the input. That's all it is. So there's 2 numbers in here that we're going to configure, and I didn't choose what they are. We can start with them just both being 0. That's fine. The deep learning frameworks like TensorFlow make an educated guess, because if you set everything to 0, you might not get good predictions at all, and you might not be able to compute a gradient. And so the guess that the TensorFlow will make is what's something that will kind of not do well in your problem, because they have no idea what your problem is, but something that is likely to have just some performance that has a non-zero gradient. It's kind of hard to say more about it than that. Okay, so all we have is 1 neuron. There's 2 configurations, the weight and the bias. So as before, we can make a prediction. So in this case, we're inputting some number like 0 or something, and it outputs some number, which is just 0. So single number in, single number out. For the loss, we're going to use mean squared error. So this is exactly like in your regular regression problem, where you take all of your line and all of your actual true data points, and you calculate the difference in the wider axis, and you square it. That's kind of your R squared, and then you average that over how many samples you have. That's what this is. So this is just squaring all the differences between what we predicted and what was actually true and averaging it all. So very, very simple loss function. In this case, that loss computes to 0.09. So delta y must have been 0.03, and then when we square that, we got 0.09.
So this is calculated based on the weight which was somehow suggested with this initial neuron.
For this purpose, it's okay to think of the weight and bias as starting at just 0, 0.
Okay.
That's okay. Like in this case, that would have worked. And so you can think that weight and bias is 0. We have a simple line, which is y equals 0. We looked at the first data point, which is not 0. And then we said, oh, there's some error. We predicted 0, and we actually had 0.3 or something.
Okay.
So now, how do we change the W and the B to get closer to that? That's the next question.
Okay.
So that's where we set up the optimizer. So again, Atom is kind of one of the state-of-the-art optimizers. What it basically does is it's exactly like that rolling the ball down the hill, where wherever you are in your loss function, you take a derivative. So we calculated some loss, 0.09 or whatever. Then we differentiate that loss with respect to the weights. So in which direction should we change the slope, and in which direction should we change the y-intercept to get closer to the correct number?
How does it know? Does it run it again somehow, or it has to? How does it know?
I'll get into that. So this is the magic of TensorFlow and stuff like that. I have some slides that go a little bit deeper in that. But you can just compute it. For our case, actually, you could. This isn't what we did here, but you could do it by hand.
Because you have to somehow compute it around the point where you are, no?
Yes, you do. 100%.
Okay.
So we could do this on paper. So like we could run this algorithm on just like a notebook, and we could write it out on paper if we wanted to. And the way it would basically look is, you have your function y equals mx plus b. That's your neuron, or in this case, wx plus b. Right. You then have an output that you predicted, right? And then we're going to square that output because of the mean squared error. So now we have y equals mx plus b squared. Now what we want to do is we want to take the derivative. So that's the loss. Loss equals the square of y equals mx plus b. So what we want to do is we want to take d loss dw, where w is the slope, right? And so that's just the chain rule, right? You take this 2 down. Now you have 2 times y equals mx plus b times what's on the inside. What's on the inside is just mx plus b. The derivative of that is mx. The derivative of that is just m. So our expression for the gradient is just 2 times y equals mx plus b times m. So that's actually the slope. And so now then the question is, well, we want that loss to go down, right? So we want to take the gradient in the direction which minimizes it. And so that gives us, that is that gradient, that is the derivative of like what is the slope. So we negate the slope because instead of going up, we want to go down, and we take a small step. And we basically, that step is just some constant, which can be just some small number because we want to take small steps. That'll be obvious why in a minute, multiplied by that gradient. And we just computed that gradient as 2 times y equals mx plus b times m.
I understand. So basically, you somehow find the kind of opposite function to go closer to what it's supposed to be.
Yeah, it's literally just the derivative. It's nothing more complicated than like, you know, it's this basic principle of, right, like when you have a function like a parabola, if you want to find its minimum, if you just compute the gradient kind of points in this direction. You go in the opposite direction, you're getting closer. And if you do that in small steps, you eventually find yourself at the bottom. Yeah. It's exactly that.
Okay.
But you're doing it not with respect to x, which is your input. You're doing it with respect to the weights, which is the w or the b. Yeah.
Okay, we can move to the next, because I really hope to put this inside of 2 hours, and we are getting close to 2 hours.
Okay. Yeah. Let's try to go a little faster. All right. So that's the optimizer compiling everything we already discussed, putting everything together. For the actual model, how to fit everything, this actually just runs that gradient descent loop. And what you'll notice is, you know, here's the learning curve. So we're seeing that our error, our mean squared error, is going closer and closer and closer to 0 over time. Again, we evaluate on our test data, which we hadn't seen before, and we see that we have a small mean squared error, small loss. It's great. And then here we actually see, okay, great. You know, here's the truth. This blue line that you can kind of barely see under there is just this silly line that starts at 0.3 and goes to 0.5. The training data is just these 10 samples along that line, and the model did exactly the same thing. And then here's the cool part. This is a printout of all of the layers in this network, along with all the weights.
That's exactly what I wanted to ask. Like, if you can see inside of this brain, if it calculated exactly the same function what we used to generate the points.
So this is the cool part. So over here, the kernel, that is our W. That's our weight. And if you remember, our slope was 0.2, and it calculated 0.196. So I got pretty close. And then the bias, that's our intercept, right? And it got 0.3021, which we were aiming for 0.3.
Cool. I had no idea you can actually find these out.
Yeah. So that's kind of the main point I want to make here, is that these dense networks, they're still in use everywhere. You know, most of the neural networks you interact with today have some number of these dense layers. And we used only this dense network plus these ReLUs to do handwriting recognition, right? This really complicated thing of 900 pixels. How do you know what number got written? It's just linear functions.
Unbelievable. Okay, let's go to the next slide. What do you have there?
Okay. So diving a little deeper into that, this is the gradient descent problem we talked about.
No, you didn't skip. Okay.
Yeah. So we saw this kind of loop. That's the basic loop. This is just another way to look at it, right? So we, you know, the J in this case is the loss. That's our mean squared error. So we started over here. So if we didn't have an intercept for our function, if we set biases to 0 and we only use the weights, it would be a one-dimensional optimization problem where you're only choosing W. Therefore, you can plot it just on the x-axis. You can plot the y on the y-axis. You would literally see a parabola because our loss is mean squared error. That's the parabola. And then we could literally plot it kind of starting at some point and then take the derivative. Same thing we derived in our heads, 2 times, in this case, wx times w. So very simple derivative. And then you just change the weight by multiplying it by that derivative times some step, and eventually you'll find this low point, which that low point will be the correct slope, the 0.2 or whatever that we decided ahead of time. Now, in our case, we optimized for 2 variables. We optimized for the weight and the bias. So it's a 2-dimensional optimization. So it looks more like this, where, you know, maybe the weights are in this direction and the bias is along this direction. And it's really a kind of 2-dimensional curve with a z kind of height. So that looks more like a mountain range. And then we can drop the ball and it can kind of like take some natural path down to the center. And the center point will be our weight is exactly our slope and our bias is exactly our intercept. Now, a little bit of how this actually works under the hood. So we actually worked through a little bit of this, and the cool thing, arguably one of the coolest things about these deep learning frameworks like TensorFlow or PyTorch or JAX or whatever, is that they do this math for you. So instead of like sitting there as an engineer and saying, okay, I have a linear function and I need to take a gradient of it. Oh, but wait, I now have an activation function on top of that. So I have to take a derivative of the activation function and then chain rule it with the linear function. And then I have to do that for 1,000 layers across 1,000 weights. Shoot me. No, I'm not gonna do that, right? Nobody has time for that. The cool thing is that the most important thing that these libraries do is they do it for you. So all you have to do is write a function. Like you can literally pick an arbitrary function like y equals sine of x times cosine of x put into tan of x divided by log of y or something, right? And you can literally say, TensorFlow, give me the derivative. And it'll actually give you the analytical derivative of that function automatically with respect to any variable. So that is the coolest thing, because you can, as a researcher, just compose these crazy functions that have convolutions and attention mechanisms like in GPT, or these dense networks, which are pretty simple, or, I mean, all sorts of architectures. I mean, people get really crazy with these things, and you automatically get a derivative from the software. And so that's kind of what this is showing. We shouldn't dive too deep into it, but basically you just apply the chain rule. So you take the derivative of the outer function, then you could take the derivative of the inner function, then the inner function, then the inner function, then the inner function, multiply the slopes, and you have the slope of that weight. And so as your deep learning framework is doing this, that's what it's doing. Like it's calculating the layer, the prediction for this layer, and then it's also calculating what is going to be that slope component. It remembers that. And then for the next layer, it calculates the actual feed forward prediction, but also what's that component of the slope, and so on and so on and so on. And at the end, it just takes all of those slopes, multiplies them together per the chain rule, and ta-da, there's your update.
Who come up with this?
Yeah, the guys who did this, like I think Jeffrey Hinton and Jan LeCun and all those people from the 80s and 90s are crazy. It's amazing. I mean, people had all of these ideas figured out in the late 80s and early 90s, and already handwriting recognition was quite good already in the 90s, but we just didn't have enough processing power to do this at a big scale. So like the convolutional network that you were shown in Edge Impulse, and that frankly is used in a lot of architectures for face recognition and person detection and segmentation, stuff like that, it's existed for 30 years. But
I remember we had this at the university. I don't exactly know if it was exactly same what you just explained, but I do remember they had ideas how it's supposed to work.
Yeah. No, the ideas were there. What wasn't there was the processing power. And then with the processing power, we got the kind of explosion. AlexNet was the first one, I think in 2012 or something, that managed to have good prediction across like 16 million pictures. And in 1 year, computer vision researchers went away from all the old techniques like par cascades and filters and custom tuned functions and all this stuff. And within like a year or two, everybody ditched that and went straight to deep learning. It really was, like that almost, where people figured out that like stacking many of these layers can be trained efficiently with a lot of compute and some careful techniques. And then it all broke out. But yeah, I mean, even that was 10 years ago. So the other point here is that these auto differentiation setups, so PyTorch, TensorFlow, JAX, they can do this not even just on a simple composition of functions, they can do it on entire graphs. So we can have an input and it can go to a convolution and a dense network, and then to a transformer, and then to whatever else. You can have these crazy branches, and then you can bring them all right back into a single number, which is how wrong are you? And then you could take a derivative of all of that. So like for scale, right? When ChatGPT says, I forget how many weights they have, like 600 billion parameters or 100 billion, I don't remember, something hundreds of billions of parameters. That means they're computing 100 billion gradients on every single time step and updating each one of those individually, right? So they're doing 100 billion derivatives for every single picture or word or whatever that they're seeing and updating it. And if you just do that a little bit at a time, 1 trillion times in a row, you get ChatGPT.
Wow.
Yeah, so just to show real quick our point about the activation functions. So let's say we now switch to training on a sinusoid. Let's say we have 10 data points. I can run this pretty quickly. So obviously, as we just discussed, without an activation function, these dense layers are just linear functions, right? So a single dense layer will never do more than y equals mx plus b. We still have only one slope, one intercept, tune, and you can see the loss quickly finds some number, but it can't get any lower. Yeah, it got better. It found the average, but that's it. That's the best we can do.
But this is exactly what I would expect. This is very nice picture actually, telling us that we can't really use only simple linear stuff, because you will never, you will get average.
Yeah, absolutely. I mean, we can even show, we can stack many of these, right? So this won't be a surprise. So I could, take out this, and this, and then we'll run this real quick. So now we have, 1,111 neurons, which means we have 2,222 configurable parameters, right? Half of them are weights, half of them are biases, that we are now changing to try to get as close as possible. So we have 4 layers, we have all these, weights, all these biases, and we train this whole thing, and you see the loss doesn't get any better. 0.4325.
It's still only linear function. Okay.
It's still only a linear function. So even though you have a crap ton of parameters, doesn't mean you did anything useful. But if we add these rectifiers, so these are just the same rectification function that we talked about. So in this case, I use the leaky value because it learns a little bit better, but it's above x equals 0, y equals x, so just identity. Below x equals 0, it's 0.3 times x. So it's a little bit of a slope. So it kind of looks like this. That's kind of what the function looks like. But this is enough that all of a sudden you see our loss is getting really small. And that gives us this.
Wow.
And if you remember, let me actually, just to make this point, oh, nope, I should have stayed around here. Let's go back, handwriting, and let's go to Colab. Our neural network that we used here, that was all it was. So the only thing we haven't talked about yet is the dropout, which I'll mention in a second. But you can, when we're done training the network, this actually goes away. So you can think of it as doing nothing. We have our dense layer, which had 256 neurons. We had an activation, which was the ReLU. So it was actually even simpler. It was just 0 below x equals 0 and x above x equals 0. And that's it. So we had 256 of those, 128 after that with the ReLU again, and then 10 for the output because we need 10 numbers to classify 10 digits. That's it. That was enough for us to recognize handwriting. Now, this last point about what is dropout is another interesting point. So one thing that can happen with these neural networks that you have to be really careful about is this problem called overfitting. So let's add a bit of noise to this problem. And what you can start to have happen is that your function gets really, really, really close to all of the individual samples in your data set, but it's really close to each individual sample rather than the true function that you really have. So hopefully this will show a good example of that here. Right here. So our function is like almost perfectly hitting every green point, right? But our truth was actually this blue curve. And so we didn't want that. So this is the problem called overfitting. This was why we were checking the validation set in addition to the training set.
So we found the exact function to fit all the points what we have, but that's not actually a real example because some of these points are noise and they are not really copying the real thing.
Exactly. So the best thing to do, and this is always true still today, the best thing to always do is more data, right? So if we just set it to 100 points, we didn't change anything else, we didn't improve anything, we didn't make the network any smarter, nothing like that. But if you at least just increase your data, these things tend to get better and better and better. So like this is the answer that nobody wants to hear in a company when you're doing supervised learning, is not to make your neural network more complicated, but to just go get more data. Because it will start to do a lot better, right? So now we're still kind of overfitting,
but we are not going through all the points.
No, at least we're not going through all the points. Now, if we made the function more and more and more complicated, so if we kept adding layers, we eventually would, hit every single point and have it be really, really, really noisy. That's definitely possible.
But we don't want to do that. That's not what we
don't want to
are
do
looking for.
Exactly. Let's even, out of curiosity, let's see if we can make that happen a little bit more. With 100 data points, it might be a little bit too much, but let's see. This won't take too long. So we don't want to do that. So if you can't have more data, there are other tricks that you can play to make your model not overfit. The simplest one is actually to make your model smaller. So if your model is really, really big, it might be too powerful. It might be too good of a universal approximator, and it'll kind of overfit everything. Well, yeah, not fitting every single data point, but yeah, not matching what we want so nicely. What this dropout does, let's actually go back to something like this. It's actually another really interesting function, and it's amazing how well it works. So what this dropout does is it takes randomly 1/10 of the neurons and kills them on every single training run. So it basically says like, hey brain, try to make this prediction, but these 10% of neurons are dead. Use the other ones. And then the next iteration, it'll choose some new set of neurons to kill, and then some new neurons and some new neurons, some new neurons. And the idea is that instead of having one kind of fragile big function that tries to predict the same number and potentially overfits, you end up coming up with like many, many, many neural pathways that predict the same thing. And then when you're done and you're actually running it in real life, you can just let the brain have all of its neurons, and then they add together into the correct prediction. So this is another interesting regularization technique that avoids some of the overfitting. And so sure enough, actually, you kind of see a little bit closer to the truth, where it's kind of forcing it to be a little bit simpler by killing off some neurons here and there. And that's what we did. So the entire handwriting example that ran on the thing, this is how we trained it. So just take that matrix of images and turn it into a single vector of length 28 times 28, which is what, 800 something pixels, 800 something numbers. Do a 256 wide linear layer. So just 256 y equals mx plus b linear functions. Apply a ReLU activation function. So just that simple rectifier. Kill 20% of the neurons. Do it again with 128. So there's actually quite a few. So it's 256 times 128 totally new functions, linear functions going from this layer to this layer. So quite a few. Then again, apply rectifier. Again, kill 20% of the neurons. Then final dense layer, 128 times 10, so 1280 weights, 1280 biases. And that's it. And that's our output.
What if you only use one layer? Is it going to be really bad?
That's a very interesting question. So
can we try it on our sinus wave?
100%. So I believe, and I don't want to speak too confidently about this because I did not look at this closely. Well, so one thing is we need at least 2 layers because our final output has to be just a single number.
Yeah, okay, I understand.
But that's okay. At least 1 layer can be like this, and let's train it. Now, I believe this will work. And if I'm not mistaken, there might even be theoretical results that show that it's possible to take any, just for dense networks, so only for these interconnected ones, any such network and rearrange it into one single wide network. And don't quote me on that because I don't remember if that was actually what I read. I saw it as a skim on Reddit somewhere. I was like, oh, that's interesting, but that's not what I use, so who cares? And I didn't pay attention to it. But yeah, there it is. So a single very wide layer. I should double check, but it might be true that it can always do the same thing that many kind of deep layers. It just might not be as efficient. So it might be better to stack, some functions in composition rather than just a very, very wide linear regressor of many, many pieces.
So it's like, for example, if you have 110 and 1 can be much more, can be same good as, I don't know, 1,000 layer.
Maybe, probably not 1,000, probably, at least 100 times 1,000, so probably at least 100,000.
Okay.
But I don't know. We'd have to work through the math to really be confident of that.
So it will use like much more neurons than if you use layers.
Right, because what's really happening is it's all about the number of weights and biases. Because when we go from layer 1 to layer 2, it's number of neurons A times number of neurons B
that's what
times
I saw.
2 configurations. Now, this is only true for these densely connected networks. If you looked at a convolutional net, or if you looked at a convolutional net, for an example, the same thing does not hold. So a single layer of 1,000 filters is not the same as 10 layers of 100 filters. They're very, very, very different. And so only in this case of the really dense networks does this trick work. But when you get into convolutions and you get into attention and all these other architectures, that doesn't apply anymore. So you need to balance the depth and the breadth of your network.
Okay, again, this is the know-how and everything what the people have to go through if they would like to come up with good AI for specific application or good model for specific application.
That's right.
Okay.
So then the final point that I just want to make is a little bit, so that was it for supervised learning. And this kind of shows, as a recap, a network is a function, just a function. It has some configuration. We are finding the best configuration to fit our data set. And we're doing it by just taking derivatives and moving all the configuration variables in the direction of those derivatives. That's supervised learning in a nutshell.
Cool.
So then how did we do reinforcement learning? So this is considerably harder. And we shouldn't go into all the bloody math that really goes all the way in through it, because it's a lot. But I want to give at least some intuition that it's quite similar. The foundations are similar to supervised learning, but the application is trickier.
Okay.
So again, reinforcement learning, we already saw an example. We want to have some game or something that has a score, and we want to keep optimizing that score, make the score better and better and better. So in our case, we had a robot, and we were just saying, walk as far as you can while being energy efficient. But many common games that you can start with when you're practicing is you can do a lunar lander. There's a lot of examples for this one. So you're starting at some point, you're falling to the ground. How do you land on the moon with as much fuel as possible? And by the way, this is not what SpaceX does.
I was actually thinking about it.
No. This is definitely not what they do. But it's kind of cool anyway. That would be too unpredictable for them. For fun, if you want to get into that, the guy who does the landings at SpaceX, his name is Lars Blackmore. He's published a lot of research of how he does this stuff, and some of his algorithms are published from when he was at JPL. So they actually also talk about the convex optimization that they do, but it's not with neural networks. It's not stochastic. It's a much more prescriptive method. But I mean, hey, that's still kind of cool. You can train a neural network to do this and almost always land successfully. Another fun one that people start with is called card pull, where you're just trying to balance a pole on a box. You could do this with a PID controller, but it's more fun to learn.
Again, that's what I was thinking about. It's probably same for the SpaceX situation, like use standard automotion, or what is it, algorithm and filters and all this stuff, rather than doing machine learning and hoping or not knowing what exactly it is doing and hoping it will always do it the right.
Yeah, in a lot of cases, if you have so this is all model-based control for SpaceX, right? You have some model of your vehicle and you're planning some trajectory. And in certain cases, you can even have provable guarantees that if everything is working correctly, that you will find a solution. So whereas with this is kind of probabilistic, right? Hopefully you get lucky, but sometimes the neural network might hallucinate and do something weird, right? We don't want that. But in simpler cases, it might be better to actually do the math and derive a specific solution that is guaranteed to exist under all circumstances. And that's obviously much better for that kind of case. And then, of course, we already saw a little bit of running, but you can play with humanoids. You can play with, you can make your own robot of however many legs you want and play with it, as we saw. So the basic loop that we're going through is we have this kind of interpreter and this agent in this environment, right? So the environment is just, here is our robot, here is the plane, it has these legs, and therefore it has these set of actions it can take, right? The agent is basically the neural network. So in this case, for us, it was the policy neural network. It basically takes in the state, So what do you currently see about your environment? It could literally be a picture of the environment. It could be, so like in this case for card pull, what you typically do is you give it the position of the base and you give it the angle of the stick with respect to the base. Those two numbers are enough for it to kind of know what to do next, right? So if it's leaning here, you want to move this way. And so that's enough information. For this guy, same thing. You give it a position, X, Y. You give it a rotation, just a single theta is fine. Maybe and then that's it. And you just compute thrust. And so then it'll control how much thrust to apply and how to rotate to then come to the bottom, right? So the neural network is taking as an input the state and spitting out these actions of what should I do. And this interpreter is basically tweaking the weights in the neural network to do that successfully. So it's kind of saying, hey, this neural network played this game and it did really bad. But this neural network played this game and did really, really good. So let's change the weights such that it is more like the one that did well, kind of. That's the kind of loop that we're going through. So for the algorithm that we use for the robot, it's not the simplest reinforcement learning algorithm, but in particular what we used was proximal policy optimization. And we shouldn't go into full detail of it, but I just want to give a little bit of an idea of how it works. And then if you really like this, get into reinforcement learning. There's a lot to learn, a lot of cool stuff. So the basic iteration loop works like this. So we actually start with kind of two neural networks this time. So we're going to use two different neural networks to do this job. One is the policy. So that was the function we talked about that takes a state and produces some action, right? So that's what we actually use to control the robot. And then the other one is called the value. And the purpose of the value is to tell the training loop how good a certain state is. So the simplest way to think about it is something like chess. And this is actually, DeepMind didn't use PPO to play chess and Go. They used something else called Monte Carlo tree search. But the concepts are close enough at our level. If you look at a chessboard, when you just look at the beginning of the game, the value of that state for either player, for black or for white, is just 50%. You're 50% likely to win the game or lose the game, approximately. But like, if I have my rooks and queens checkmate on 1 on your single, not king, then probably the value is close to 1 for the white player, because 1 move and I'm going to win. It's like impossible for me not to win. So the value of that state is really high for white. So as you can play, if you have this function that can measure for you how good is the state you're in, you can use it to make decisions, and you can use it to train a policy. So that's kind of what we'll do. We have this function that actually predicts the motion we should make, and we have a function that tells us how good is our current state. Are we likely to get a good score at the end? So at this point, they're both random. Then we iterate. And so here in words, I just simply rewrote this kind of more mathy algorithm into just kind of intuition. So the first thing we do is we collect trajectories given a simple policy. So at first, our policy network is randomly initiated random weights. We spawn 1,000 simulations and we say, robot, go run. And 1,000 robots wake up and they run and they do random twitching, right? They're not doing anything useful. And then for each one, we will compute the reward. So for each one, we'll say, how far did you get, right? And so some of them will have gotten nowhere while spending a whole bunch of energy. Some of them will have gotten a little bit further away. Okay. Then we compute this thing called the advantage. So the intuition of the advantage is that it is kind of telling you, for the tweaks that you've made to the policy, how much better is it performing than the previous policy you had? So we want to kind of measure, did you improve or not improve the policy? Now, at this point, we've only done one iteration, so we don't have an old policy. But now let's pretend we're on the second loop where we have an old policy and a slightly updated policy. We'll talk about the update in a second. And the way you do that is you kind of compare the current policy's outcome, like the total reward of that policy given that state, with the value function that you also trained. Because you're training the policy and the value at the same time. Your value is kind of telling you how good the old policy would have done at that state. But now you have a new policy that did better or worse than that. And so that tells you whether or not you should be more like this new policy or less like this new policy. So that's kind of the intuition of the advantage function. We then update the weights of the policy network. So we want to maximize the probability of actions with high advantage. So those actions which led to a good reward, which therefore led to a good advantage, we want to maximize the chance that our neural network predicts those actions in those states. And of course, you want to implicitly do the opposite. You want to avoid, the actions that ended up leading to bad outcomes.
Mm-hmm.
You also, another critical thing here, and this is kind of the genius part of this PPO algorithm, is the clip part, which is where you actually don't want to update the policy too much. Because if you kind of think about it, like if you're, there's this funny example that a lot of these lectures show, was basically like a person riding a bike on a big hill, and if they go down the middle, they're okay, but if they turn too far left or too far right, they fall off the cliff. So you don't want to turn so hard to the left that you fall off the cliff and go into some new policy that's performing really badly. Presumably, your old policy is already okay, and you just want to improve it slightly. So you limit the extent to which you make that improvement. And so that's where this clip comes in, where if you see that the change is a little bit larger than you would want, you just cut that change. You say, okay, no more than this change. And that kind of makes it so that, like, if your bike is turning left around some obstacle, instead of turning way left and falling off the cliff, it turns a little bit more left to avoid that obstacle. And that's kind of like keeping you close to where you were. And then you update the value neural network. And so this is basically just, hey, we had this state. From this state, after our policy played a bunch of different games, this was the average outcome. So therefore, this state is this good. So you kind of updated both at the same time, and then you just repeat. So you're always keeping track of, like, how do you update the function that predicts the action given the state? That's the policy. And how do you update the function that predicts how good the current state is? That's the value.
It's interesting.
And a lot of times.
Yeah, it's interesting. Sorry. They give you this algorithm because otherwise it would be so complicated.
Oh, yeah. Writing this from scratch it's a very good exercise to do, but it's not easy.
But I interrupted you. What do you wanted to say?
Just one final point is that in most implementations, the policy and value neural network are actually the same. So you have the same set of kind of early layers. So like in AlphaGo, when they played Go against Lee Sedol with Monte Carlo tree search, they actually used a convolutional neural net. So it had those convolutional layers, just like you were talking about with the previous video. It had, activation functions. It was something simple like the RailUse or something like that. I don't remember exactly. They condensed it into dense layers at the end, and then that's actually, maybe they didn't. They might not have condensed dense layers for the policy, but for the value they did. But the interesting thing that they did is the value in the policy network was one same thing for 40 layers. And then they actually, instead of predicting a single number out of that, they predicted two. So one side of it split into, here is the Go board, here's where you should place the next stone. And then the other one split into some dense layers that just predicted, here's the value of this Go state. So the policy and value network can actually be largely the same network, except for it diverging in the last couple of layers. Because if you think about it, the same features you would want to predict the next move are probably the same features you would want to predict how good your current position is.
Can we see how you use this PPO algorithm in our example? I just would like to see the command.
Yeah. So thankfully, I didn't have to write it from scratch or anything like that. So it's all kind of under the hood, but we can dive into it just for a second to show some intuition. So here's our notebook. This is just the Brax notebook. Well, I guess you wanted to see the hexapod. So let's do that one. Here's
I guess it's used in both examples, no?
It's same thing. Yeah, it's exactly the same thing. So this is the hexapod. This was our model. I changed the reward because I wanted it to walk slowly. So that was what happened here. But I didn't actually do anything myself with PPO. I just used their function and said, please train.
Where did you use it?
So we have, this is PPO.train. That's the function right there.
And these are the parameters, or how did you need to send something
these are
there, no?
Yeah, so these are the hyperparameters. So basically when you train PPO, you have the actual weights and biases of the neural network on the inside. And in our case, I didn't even choose the neural network architecture. Brax already has a reasonable network architecture inside their source code that when you call PPO of that train, it just uses that. Now, if you want to, of course, you can specify your own network, you can feed it in, and you can train your own architecture. For our case, I just didn't have to. It was easier to just use what they had built in. So the weights and biases are being determined by a PPO doing its iteration. But there's also these things called the hyperparameters. And this is the case both in supervised learning and in reinforcement learning. So a simple example of a hyperparameter is how, like, let's go back to the handwriting problem of our dense layers. How many dense layers do you want to have? Do you want to have 1 layer, or do you want to have 3, or do you want to have 10? Yeah, that's a hyperparameter. How wide do you want your dense layers to be? Do you want it to be 1,000 or 100 neurons or 100,000 neurons? That's another hyperparameter. Those are all choices that you and I can choose. Now, of course, software engineers, being the lazy people that they are, don't want to choose those either. So what you do in a typical production setup is you do optimization on those choices as well.
So you run it with, I don't know, 2 layers, 3 layers, 5 layers, and then you find out, okay, 3 layers are exactly what is good enough for what we need.
Exactly. Yeah, so you can do that by hand. You can, get an intern and then have them run it all, right? You can do it in a grid. So you can just say, I want to try 2 layers, I want to try 3 layers, I want to try 5 layers. That's another reasonable choice. Or people also get clever. So you can do this thing called Bayesian optimization, where you basically try 3 layers, see how well your validation accuracy and score was and everything like that. Then try 5 layers and then see if that improved it or decreased it. Make a small Bayesian model that tries to predict how your performance is being altered as a function of that choice of the number of layers. And then it can make the next prediction. It can say, oh no, go back to 1 or try 10 or try 7. And so that's just a little bit faster than trying everything in a grid. Because trying everything in a grid, typically if these things are taking hours or days to run, you're not going to have enough time. So you can use a slightly smarter statistical method to try many hyperparameters. And the nice thing is that the nice folks over at Google did that for us, and that's how they came up with all these numbers. So going through these real quickly, it's like number of time steps. Okay, we're evaluating for 50 million. How many evaluations are we doing? I think it's just keeping track of like how many environments we're running just to keep metrics. What's the length of the episode? So that's like how many time steps there are in this thing. Whether you want to normalize your observations. So do you want it to be 0 to 1, or do you allow them to exceed that range? Do you repeat actions or not? So do you send the same action into the simulator twice or just once? How much do you unroll? So like when we train these models, we're not actually just training on a single state and action. We're training on a set of states and actions, because it was like state 0, action 0, state 1, action 1, state 2, action 2, all the way through 1,000. That's what constitutes the whole game, right? And so you might want to take small samples of those sequences and train on those. That's what that's choosing. Mini batches are how many environments you're doing at the same time. Update, blah, 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 blah. Discounting is like...
all of them.
I have to.
So if you like, very quickly, you can also explain a little bit about what you are doing.
Sure.
You can open your company website.
Yeah, totally. We have a new website coming soon, so unfortunately you'll get to see the old one, but that's okay. In a couple of weeks we'll have a new one. But yeah, I can just show the fun part, which is the boards. So on our blog we have some of the boards that we've designed, and all of these boards are fully compiled by machine. So the idea is that you take your, actually the last page is a good example of this. Do your schematic like normal. So just like the same thing you've always done, same as before. Then you define your constraints. So you draw the outline of your board. This is KiCad, by the way, but we support KiCad, Altium, and Eagle. You can place some of your components. So actually this is this board, this OpenMV board that I'm drawing out. And that connector up there is this camera. And then there's the actual connector right there. And then that connector that I just placed there's a power connector on here, which we didn't populate. And then that one is the USB, so on and so on and so forth. So you kind of just draw like the outline, place your connectors, and anything that you like your screen that you really want the position to be in a specific place. And that's it. So you submit that. And then we generate a whole bunch of layouts. So we go through and we create a whole bunch of candidates, thousands and thousands of them. We try multiple stack ups. So we'll try 2 layers, 4 layers, eventually 6, 8, 10, whatever. We try all sorts of manufacturing rules. So we can try to use like 10 mil traces for everything. But like if we can't quite get that to work, we'll go down as low as 3 mils. But we are making sure that whatever manufacturer we're trying to compile for, that this board will meet all their rules. So for right now, we simultaneously target JLC PCB, PCB-way, and OSH-Park. But we also use some generic rules like 10 mil trace, 10 mil clearance that for simple boards, anybody can manufacture. So you don't have to set your design rules. And then what we're eventually, we haven't fully closed the loop on this yet, but what we also do is we run 3-dimensional physics simulations. So full wave electromagnetics that's actually computing the currents and the fields and everything for your board. And then with that, we will, so you can actually already run the simulation in our tool. You can upload a board and just see like the S parameters for, insertion loss or some, transmission line on a board, or crosstalk if you want to. And over time, we will add that in to teach the neural networks how to avoid issues. So how do you avoid your switching power supply from coupling into your clock line and minimize that as much as possible? And then over time, these neural networks will get better and better at avoiding running the clock line under a switching converter and all the other different issues.
We really should try this on some of the boards what I designed in my tutorials. That would be fun.
Yeah. So actually, I think I saw that you have one that is the Arduino Uno.
Yeah.
That's one of our examples. So if you come sign up for the Quilter waitlist, we have an Arduino Uno for you ready to go in Eagle, and you could do it in Altium if you want to, and just upload it. And the only thing we have is the connector, the power supply in the right place, and the headers, and that's it. We do everything else. So this one was an older design. We did this in like October of last year. We've seen since the compiler's gotten much better. But I mean, we built it and it works. So we actually fully did the layout. As a rule, whenever we post the board on our blog, no human will have touched any copper. So that's a rule that we hold ourselves to. Only connectors, only board outline. That's it. All the traces, all the pours, all the layer stack up, all the clearances, all the design rules, the DRC, 100% computer generated.
We have to stay in touch.
Of course. Schematic, blah, blah. You can read the blog. It's super fun. This is the inputs. So like I said, only place the connectors and so on and so forth. And then this is the candidate that we got. This one was compiled for all 3 fabs, so you could manufacture it wherever you like. And then of course we, made sure it works. So, write some basic code and run a loop. And then I also, this was fun, I connected a screen to it just to do some handwriting. But we've got a few boards on here. So we've got that one. Today we actually saw the computer vision board. So this one's faster because the STM32 is actually running at a pretty good speed. It's got USB, it's got SD card reading pretty fast. So we already saw that one today. And we've got a couple of more that we've done, and we're going to post a lot more. This one was an audio board. So this is an amplifier that takes in either digital MP3 from a SD card or a raw analog signal and just drives these speakers based on one of the Adafruit boards. And then we also have a motor controller because we started getting into some more high power stuff. So, we got to start getting better and better at supporting higher currents. So we got this board that basically drives a stepper or a DC and gets pretty hot. This chip itself is 72 Celsius, I think, when it runs. But again, board works fine. I haven't burnt myself, so it's working okay. And we've got a lot of boards coming. We've got a bunch of collaborators that are showing us some of the boards they want to do for open source, some boards for companies, and some boards that we're doing internally, like network controllers and stuff, are going to be up next. So we're definitely not done. Like if you come and upload a motherboard or something, no chance this is going to work, but we'll get there.
Okay, I will try.
Yeah, welcome to. Yeah, so the kinds of boards that you're seeing are roughly what we're currently best at. So, no more than 100 components, no more than 600 or 700 pins. Most of our layouts end up being 4 layers. No more than an amp or 2 of current.
I have a board like this.
Perfect.
Yeah, come try. If you like, we can try it together then and have fun together.
Sure, for sure. The only thing is that we can't do it in this video because it's not that fast. If you have a really trivial board, it takes us 10, 15, 20 minutes. But if you have a complex board, it can take a few hours.
Yeah.
So I don't want to keep it for that long.
No
But
problem.
you're welcome to try.
I'm just curious.
Yeah, of course.
Okay. Thank you so much, Sergiy, for all these explanations. And it was super helpful. Again, I learned a little bit more about machine learning, and I really hope maybe I will, in future, when I play with it, I will understand much more what I can change and what everything is doing, not just trying to repeat tutorials and not really understanding what I'm doing.
Yeah. Hey, hit me up if you have questions. I'm happy to help. There's a really good community online of people helping each other with deep learning. So you'll find forums and Reddits and papers and everything. It's really great. The community is really thriving.
But it's very hard to find someone who really understands what is actually happening and how it works. That's why I'm so thankful for your time and helping me to create this video. So thank you again, Sergiy.
Awesome. No, thank you for having me. It was fun.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.